April 1943. A remote airfield in Japanese-occupied New Guinea. A group of elite Japanese Navy pilots stood in silence, circling an aircraft unlike anything in their inventory. The twin-boom design was unmistakable. The sleek, deadly profile was infamous throughout the Pacific. This was a Lockheed P-38 Lightning, the aircraft they called the fork-tailed devil. But this P-38 wasn't attacking them. It sat motionless on the tarmac, captured intact after an emergency landing. And now, Japanese intelligence officers wanted their best pilots to do something extraordinary: fly it. The Japanese Navy's top evaluation pilot, one of Japan's top aces with over 60 kills, walked slowly around the aircraft. His hand traced along the polished aluminum skin. He examined the twin Allison engines, the distinctive twin booms, the central nacelle housing the cockpit and weapons. "It's larger than I expected," the ace said quietly to his wingman. "Heavier. The Americans built this for power, not agility." His companion, Lieutenant Hiroyoshi Nishizawa, another ace, laughed. "Of course. The Americans don't understand fighter combat. They build heavy, clumsy aircraft and rely on speed and firepower. Our Zeros will dance circles around this machine." The lead pilot wasn't so sure. He had fought P-38s in combat. He had watched them climb away from his Zero at impossible angles. He had chased them in dives and watched helplessly as they pulled away, faster and faster, until they were specks in the distance. The P-38 was more than just another American fighter. It was a mystery. A threat that Japanese pilots couldn't fully counter. And now, for the first time, they had a chance to understand it from the inside. Within days, this ace would fly this captured P-38. He would push it through combat maneuvers, test its limits, feel its power, and what he discovered would shake his understanding of aerial warfare. This is not a story about Japanese engineering versus American engineering. This is a story about a moment of brutal clarity. When experienced combat pilots, some of the best in the world, flew an enemy aircraft and realized they had been fighting an opponent they had fundamentally misunderstood. The P-38 Lightning wasn't just a different fighter. It represented a different philosophy of air combat, a different approach to technology, a different vision of what a fighter aircraft should be. Japanese fighters like the Zero prioritized maneuverability above all else. Light weight, tight turning radius, maximum agility in close-range dogfights. This philosophy came from Japan's experience in China, where aerial combat happened at low altitudes and close quarters. The Zero was perfect for that kind of fighting. But the P-38 was built for a different kind of war. Long-range strikes, high-altitude interception, boom and zoom attacks that exploited speed and altitude advantage. It was designed to fight in the vast expanses of the Pacific, where range mattered as much as maneuverability. And the Japanese were about to learn that their approach, their doctrine, their entire understanding of fighter combat was being rendered obsolete by American technology and tactics. The evaluation pilot's final report would state that flying the captured P-38 was one of the most significant moments of his combat career. Not because it was enjoyable, not because it was impressive, but because it was terrifying. It was terrifying to realize that the aircraft he had been fighting, the aircraft he thought he understood, was far more capable than Japanese intelligence had believed. It was terrifying to feel the raw power of those turbocharged engines. It was terrifying to experience the speed, the climb rate, the ceiling that no Japanese fighter could match. But most terrifying of all was the realization that came after the flight. The understanding that Japan was fighting an enemy with technology they couldn't replicate and production capacity they couldn't match. The P-38 wasn't a miracle of engineering. It was the product of American industrial might combined with advanced aeronautical knowledge that Japan simply didn't possess. Over the next several weeks, Japanese engineers and pilots would conduct the most thorough evaluation of an enemy aircraft in the Pacific War. They would disassemble systems. They would analyze manufacturing techniques. They would test performance in every flight regime, and their reports would make uncomfortable reading for the Japanese high command. Because the P-38 Lightning represented more than just a good fighter aircraft. It represented a technological and industrial gap that was widening every month. While Japan struggled to produce enough aircraft to replace combat losses, America was building P-38s by the thousands. While Japanese pilots flew fighters with minimal radios, limited instruments, and no armor protection, American pilots had sophisticated equipment, excellent communications, and protection that kept them alive. The captured P-38 became a symbol of a harsh truth that many Japanese officers didn't want to acknowledge. They were losing the technological war. And in modern aerial combat, technology mattered more than courage or skill. This is the story of that captured P-38. The Japanese pilots who flew it. The engineers who analyzed it. And the devastating conclusions they reached about Japan's chances in the Pacific War. It begins with a forced landing in the jungle. And it ends with Japanese pilots admitting what they had feared but hoped wasn't true. The Americans had built a fighter they simply could not match. The fork-tailed devil was about to reveal all its secrets. And those secrets would haunt Japanese aviation for the rest of the war. The story of how Japan acquired an intact P-38 Lightning begins on December 27, 1942, over the jungles of New Guinea. Second Lieutenant Robert Farreau was on a patrol of P-38s from the 39th Fighter Squadron, operating out of Port Moresby. Their mission was routine: sweep the coast for Japanese shipping and provide top cover for Allied positions. But routine missions in the Pacific had a way of becoming complicated very quickly. Approximately 1,400 hours, Farreau's aircraft encountered heavy weather. Tropical storms in New Guinea could appear with terrifying speed, turning clear skies into walls of rain and turbulence in minutes. The flight made the decision to climb above the weather, taking his flight to 22,000 feet. It was a sound tactical decision. But it came with a cost: fuel consumption. The P-38's twin Allison engines were powerful, but climbing through weather burned fuel rapidly. By the time the flight cleared the storm system, Farreau's fuel gauges showed less margin than he liked. They still had enough to make it back to Port Moresby, but there was no reserve for combat or extended maneuvering. Then his aircraft reported engine trouble. The left engine was running rough. Oil pressure was fluctuating. Temperature was climbing. Farreau tried adjusting the mixture, checking the turbocharger controls, running through emergency procedures. Nothing helped. The engine was failing. His flight leader had to make a decision. They were deep over Japanese-held territory. Farreau could shut down the left engine and try to make it back on one, but the P-38, despite its twin-engine safety margin, was not easy to fly on a single engine. It required constant rudder pressure and careful power management. Over hostile territory, in marginal weather, it was dangerous. The other option was to find a place for Farreau to set down and hope for rescue later. The flight leader chose the latter. He ordered the flight to descend and began searching for any possible landing site. The jungle below was unforgiving. Dense canopy. No clearings. No roads. Just endless green broken occasionally by rivers and swamps. Then Farreau's left engine caught fire. There was no more time for searching. Farreau had to get the aircraft down immediately. He spotted what looked like a relatively flat area near a riverbank. It was barely 100 meters long, covered in low vegetation, but it was the only option. Farreau brought the P-38 in with the burning engine shut down and feathered. He had no flaps, no proper approach speed, just a desperate controlled crash into the jungle clearing. The P-38 hit hard, bounced, slammed down again. The landing gear collapsed. The aircraft slid through vegetation, both propellers chewing into the soft ground, finally coming to rest against a stand of trees. His flight leader circled overhead, watching. The fire in the left engine had gone out during the crash. Farreau climbed out of the cockpit, waving to show he was uninjured. The leader waggled his wings in acknowledgement, but there was nothing more he could do. His own fuel state was critical. He had to leave Farreau behind and hope that rescue forces could reach him before the Japanese did. They didn't. Japanese ground forces in the area had heard the crash. Within 2 hours, a patrol from the 20th Infantry Division reached the crash site. They found Farreau hiding in the jungle nearby and took him prisoner. More importantly, they found the P-38 remarkably intact. The crash had damaged the landing gear, bent both propellers, and caused some buckling in the left boom from the engine fire. But the airframe was largely undamaged. The engines, though they would need work, were complete. The weapons were intact. The instruments, radios, and systems were all there. The Japanese patrol commander immediately recognized the intelligence value. He radioed his headquarters, and orders came back quickly: secure the aircraft. Guard it. Engineering teams are en route. Within 24 hours, Japanese engineers arrived at the crash site with cutting equipment and heavy tools. They spent 3 days carefully disassembling the P-38 into transportable sections. The wings were removed. The tail booms were detached. The central nacelle with its cockpit and weapons was separated. Everything was carefully documented and photographed. The components were then transported by truck to the coast, loaded onto a barge, and shipped to Rabaul, the major Japanese base in the Southwest Pacific. The journey took nearly 2 weeks, with the precious cargo guarded at every stage. Rabaul, Japanese Navy technical intelligence officers took charge. This wasn't just another captured aircraft. The P-38 had become a serious problem for Japanese forces throughout the Pacific. It appeared everywhere, escorting bombers, conducting long-range fighter sweeps, ground attack missions. And Japanese pilots struggled to counter it effectively. The P-38 was fast. Too fast for Zeros to catch in level flight or in a dive. It climbed better than anything in Japanese inventory. It had phenomenal range. And its firepower was devastating. Japanese pilots reported that a single burst from a P-38 could disintegrate a Zero or Betty bomber. But intelligence about the P-38's capabilities was fragmentary. It came from pilot reports, often made in the chaos of combat. No one in Japan truly understood why the P-38 performed the way it did. What made it so fast? How did it achieve such high-altitude performance? Why couldn't Japanese aircraft match its climb rate? Now, finally, they had a chance to find out. The damaged P-38 was carefully reassembled in a hangar at Rabaul. Japanese mechanics worked from photographs and technical drawings, piecing it back together like a giant puzzle. The bent propellers were replaced with props salvaged from other crashed P-38s. The damaged landing gear was repaired using parts fabricated in the base machine shop. It took 6 weeks of intensive work, but eventually, the P-38 was structurally complete again. The left engine, which had suffered fire damage, was deemed reparable. Japanese mechanics who had worked on captured American aircraft before were assigned to overhaul it. They replaced burned wiring, cleaned carbon deposits, replaced damaged accessories. It was painstaking work, made harder by the fact that they lacked proper tools and manuals. The right engine had survived the crash with minimal damage. After a thorough inspection and some minor repairs, it was deemed airworthy. By late May 1943, nearly 5 months after the crash, the P-38 was ready for ground testing. Japanese mechanics fired up the engines for the first time. The Allison V-1710s coughed, sputtered, then roared to life with a sound that echoed across the airfield. Japanese personnel who had never heard American engines running at full power stopped what they were doing to watch. The sound was different from Japanese engines. Deeper. More powerful. The twin engines created a distinctive thrumming that could be felt as much as heard. The ground tests revealed that the P-38, despite its crash landing and hasty repairs, was mechanically sound. Both engines ran smoothly. Control surfaces moved properly. Systems functioned. The aircraft was flyable. Now came the crucial decision: who would fly it? Japanese Navy Command selected their best available pilots for the evaluation. The lead evaluation pilot was the obvious choice. He was one of Japan's top-ranking aces, with over 60 confirmed victories. More importantly, he had fought P-38s multiple times and survived encounters that killed other Japanese pilots. He understood the P-38's tactics, its strengths, its apparent invulnerability to conventional Japanese fighter attacks. Joining him would be Lieutenant Hiroyoshi Nishizawa, another top ace, and several other experienced fighter pilots who would observe the flights and conduct their own evaluations. The evaluation team also included engineers from the Mitsubishi and Nakajima aircraft companies. These were the firms building Japan's fighters. If there was anything to learn from the P-38's design, anything that could be incorporated into Japanese aircraft, these engineers needed to identify it. On June 2, 1943, everything was ready. The captured P P-38 sat on the Rabaul flight line, repainted in Japanese markings to prevent friendly fire incidents. The lead ace stood beside it, studying the aircraft he was about to fly for the first time. He had flown many different aircraft types during his career. He was confident in his abilities as a pilot. But as he looked at the P-38, he felt something unusual: apprehension. This was the aircraft that had killed so many of his comrades. The fork-tailed devil. Now he was about to discover its secrets from the inside. A Japanese ground crewman approached with a parachute and flight gear. The pilot strapped in, then climbed the ladder into the P-38's cockpit. The moment of truth had arrived. The lead evaluation pilot settled into the P-38's cockpit and immediately noticed how different it felt from his beloved Zero. The cockpit was spacious, almost luxuriously so compared to Japanese fighters. He could move his shoulders freely. There was room for his legs. The seat was comfortable, with cushioning and adjustable positioning. In the Zero, pilots sat in cramped, Spartan cockpits where every cubic centimeter was sacrificed for weight savings. But the pilot's first thought wasn't comfort. It was weight. "This cockpit alone probably weighs as much as our entire tail section," he muttered to himself. The instrument panel sprawled before him, packed with gauges, switches, and indicators. Far more than any Japanese fighter. The ace counted quickly: airspeed, altitude, vertical speed, turn and bank, artificial horizon, compass, 2 sets of engine instruments for the twin engines, fuel gauges, oxygen system indicators, radio controls, electrical systems. Japanese fighters had instruments too, of course, but nothing like this level of detail. The Zero's panel was minimal by comparison. Basic flight instruments and engine gauges. Japanese doctrine emphasized pilot skill and instinct over instrument flying. Looking at the P-38's panel, the pilot understood something immediately. American pilots flew by instruments. They trusted their gauges more than their instincts. This was a completely different philosophy. He reached forward and touched the control wheel. It was a yoke-style controller, like a bomber, not a stick like fighters. Another unusual choice. The yoke felt solid, well-made, with excellent grip surfaces. A Japanese engineer stood on a ladder beside the cockpit, pointing out controls and explaining systems. The engineer had studied captured P-38 manuals and translated portions into Japanese. "The throttles are here, on your left," the engineer explained. 2 throttles, 1 for each engine. They must be kept synchronized manually. The propeller pitch controls are just behind them. Mixture controls below those. The pilot nodded, his hands moving over the controls, memorizing positions. Managing 2 engines would require attention and coordination that single-engine fighters didn't demand. The landing gear control is here. The flaps here. The gun trigger is on the control yoke. The weapons are nose-mounted, which means no convergence concerns. What you aim at, you hit. That was interesting. Japanese fighters mounted guns in the wings, which meant the bullets converged at a specific distance, typically 200 meters. Closer or farther than that, and your accuracy suffered. The P-38's nose mounting eliminated that problem entirely. Fuel management is complex, the engineer continued. Multiple tanks. You must switch between them to maintain balance. And there are drop tank controls for the external fuel tanks. The ace was beginning to appreciate the complexity of the aircraft. The Zero was simple. You started the engine, took off, and flew. Managing the Zero was intuitive. The P-38 required active systems management. More to think about. More to monitor. More that could go wrong. But also, potentially, more capability. Before starting the engines, the evaluation pilot climbed back out and walked around the P-38 one more time with Lieutenant Nishizawa and the engineering team. They wanted to make final assessments before the test flight. The twin-boom design was still striking. From the front, the P-38 looked aggressive, purposeful. The central nacelle housing the cockpit and weapons sat between 2 long booms that extended back to support the horizontal stabilizers and twin vertical tails. Why this design? Nishizawa wondered aloud. It's so unusual. So complex. The structural weight must be enormous. One of the Japanese engineers, a senior Mitsubishi designer, had been studying the design carefully. "I believe it's to accommodate the turbo-superchargers," he said, pointing to the rear of each boom. "See here. These large scoops at the back of each boom. Those are air intakes for the turbo-superchargers. By placing them in the booms, they keep the hot exhaust gases away from the cockpit and fuel tanks." The engineer traced his hand along the boom. "It's actually quite clever. The turbochargers require significant airflow and generate tremendous heat. Mounting them remotely solves cooling problems. And the twin-boom layout also allows for the nose-mounted weapons without worrying about synchronizing guns to fire through a propeller arc." The lead pilot considered this. The design seemed overly complicated, but the engineer was right. It solved several problems simultaneously. American engineers had approached the design differently than Japanese engineers would have. Not necessarily better or worse, just different. The engineers measured and photographed everything. The wingspan, 52 feet. Much wider than a Zero's 39 feet. The length, 37 feet. The weight, they estimated from examining the landing gear and structure, was probably around 14,000 pounds fully loaded. Zero weighed less than 6,000 pounds. "It's more than twice as heavy," Nishizawa said, shaking his head. "How can it possibly be effective in combat? Weight is the enemy of maneuverability. The Americans have built a flying truck." But the lead ace wasn't so sure. He remembered combat encounters with P-38s. They didn't fight like heavy aircraft. They climbed like rockets. They dived away at speeds that seemed impossible. They turned adequately, if not brilliantly. Weight clearly wasn't crippling them. The answer, he suspected, was power. Those two Allison engines. He walked up to examine them more closely. Each engine was massive compared to Japanese radial engines. The V-1710 was a liquid-cooled V-12 configuration, producing over 1,000 horsepower per engine. 2,000 horsepower total, driving the aircraft's 14,000 pounds. Japanese fighters like the Zero used a single radial engine producing around 1,000 horsepower to drive 6,000 pounds. The power-to-weight ratios were similar. The Americans just worked at a completely different scale. "They're not trying to build a lightweight fighter," the lead ace said to Nishizawa. "They're trying to build a powerful fighter. Everything is bigger, heavier, stronger, but with enough power to make it work." The propellers were another revelation. They were large, over 11 feet in diameter, and they counter-rotated. The right engine's propeller turned clockwise, the left turned counterclockwise. The senior engineer explained the significance. Counter-rotating propellers eliminate torque effects. In a single-engine fighter, the propeller torque tries to roll the aircraft. Pilots must compensate with rudder and aileron. But with counter-rotating props, the torques cancel out. The aircraft flies straight with no compensation needed. It was a sophisticated solution to a problem Japanese engineers accepted as unavoidable. Again, different thinking. The Americans added complexity to eliminate a handling characteristic, while Japanese engineers trained pilots to deal with it. The wings drew particular attention. They were thick, with a distinct airfoil shape. Not the thin, efficient wings of Japanese fighters, but substantial structures that clearly housed significant internal volume. Fuel tanks, the engineer noted. And probably quite large ones. This explains the P-38's legendary range. The wing leading edges had intercoolers for the turbo-supercharger system. More complexity. More weight. But apparently, more capability at high altitude. Landing gear was robust, almost overbuilt. Thick struts, large tires, heavy mechanisms. Designed to handle the aircraft's weight on rough airfields. Japanese fighters used minimal landing gear, just strong enough to work. The P-38's gear could probably survive much harder landings. The overall impression was clear. The P-38 was engineered with generous safety margins. Everything was stronger than minimally necessary. Heavier than optimal. More complex than elegant. But also more capable of surviving damage, operator error, and harsh conditions. It's a brute force approach, Nishizawa observed. They're not trying to optimize every gram of weight. They're just building it strong and powerful. The lead ace nodded slowly. Which means they can produce them with less precision. If you have safety margins built in, manufacturing variations don't matter as much. Parts don't need to be perfect, just good enough. This was becoming a theme. The Americans seemed to design for mass production and field durability rather than maximum theoretical performance. The Japanese engineers were particularly interested in the construction methods. They examined rivets, seams, and panel joints carefully. "Look at this," one engineer called out, pointing to a wing panel joint. "The rivets are not perfectly aligned. The spacing varies slightly. On our aircraft, this would be unacceptable." But the panel was solid. The rivets held. Slight imperfections in alignment didn't affect structural integrity. Another engineer examined the aluminum skin. "The surface finish is rough compared to our standards. You can see tool marks. Slight waviness in the panels. Again, this would not pass our inspection." Yet the aircraft flew. It flew very well, according to combat reports. "They're trading perfection for production speed," the lead engineer concluded. "Every minute spent aligning rivets perfectly is a minute that could be spent building another aircraft. If the rivets hold either way, why waste the time?" It was a philosophy that made Japanese engineers uncomfortable. They took pride in craftsmanship, in precision, in elegant solutions. The P-38 represented something different, engineering pragmatism over engineering artistry. The lead pilot checked his watch. They had been examining the aircraft for over an hour. It was time to fly it. He climbed back into the cockpit, strapped in, and began the startup procedure. The Japanese engineer talked him through it step by step. Battery on. Fuel pump on. Mixture rich. Propeller full forward. Throttle cracked open. Energize starter on the left engine. The left Allison coughed, the propeller jerked, then the engine caught with a deep rumble. The pilot advanced the throttle slightly, and the engine settled into a powerful, steady idle. Now the right engine. The same procedure. The right engine started smoothly, its propeller spinning up in the opposite direction from the left. The ace sat there, both engines running, feeling the power vibrating through the airframe. The sound was impressive. Intimidating, even. This was the sound that Japanese soldiers heard before P-38s appeared overhead, guns blazing. He checked the instruments. Oil pressure good on both engines. Temperatures rising normally. All systems showing green. The tower cleared him for takeoff. The pilot released the brakes and advanced the throttles smoothly. The P-38 began to roll. It accelerated quickly despite its weight. The power was phenomenal. The tail came up early. At 70 miles per hour, the pilot pulled back gently on the yoke, and the P-38 lifted off smoothly. And in that moment, as the landing gear retracted and the P-38 climbed away from Rabaul, the lead evaluation pilot began to understand what Japanese pilots were really facing in the Pacific skies. This wasn't just another fighter aircraft. This was something entirely different. As the evaluation pilot climbed away from Rabaul at full power, the first thing that struck him was the acceleration. The P-38 didn't just climb. It surged upward like it was being pulled by invisible cables. He leveled off at 5,000 feet and glanced at the rate of climb indicator. Over 3,000 feet per minute. His Zero, in perfect condition with an experienced pilot, could manage about 2,500 feet per minute at best. But that was just the beginning of what would be a series of shocking discoveries. The ace continued climbing, testing the aircraft's performance at different altitudes. At 10,000 feet, the P-38 was still pulling strong. At 15,000 feet, where Japanese fighters began to struggle for power, the P-38 seemed completely unaffected. At 20,000 feet, something remarkable happened. Instead of performance degrading, it actually improved. The pilot pushed the throttles forward and felt the engines respond with increasing power. The airspeed climbed. The rate of climb actually increased. This made no sense according to everything the pilot knew about aircraft performance. At altitude, air was thin. Engines produced less power because there was less oxygen for combustion. Every pilot knew this. Yet the P-38 was performing better at 20,000 feet than it had at 10,000 feet. The answer lay in those bulky installations at the rear of each boom, the General Electric turbosuperchargers. After landing, the pilot immediately sought out the engineering team. "The engines gained power at altitude," he reported. "How is this possible?" The lead engineer had been studying the captured technical manuals. What he explained left the assembled pilots and engineers stunned. "The Americans have developed a sophisticated forced induction system unlike anything we have," the engineer began. He led them to the P-38, pointing to the large scoop at the rear of each boom. "These are not simple superchargers like we use. These are turbosuperchargers. They use the engine's exhaust gases to drive a turbine, which compresses incoming air before it enters the engine." He sketched a quick diagram. Exhaust gases that would normally be wasted are routed through this turbine wheel. The turbine spins at enormous speeds, perhaps 60,000 RPM or more. It drives a compressor that forces air into the engine at pressure. The Japanese engineers crowded around, trying to understand. "Our fighters use mechanical superchargers," one engineer noted, "driven directly by the engine. But those consume power to operate. There's always a parasitic loss." "Exactly," the lead engineer confirmed. "A mechanical supercharger uses perhaps 100 horsepower to drive itself. That's 100 horsepower not available for propulsion. But a turbosupercharger uses waste exhaust energy. There's no parasitic power loss. The engine produces full power, and the turbosupercharger adds boost on top of that." The ace was beginning to understand. So at altitude, where the air is thin, the turbosupercharger compensates by forcing more air into the engine? Precisely. At sea level, the engine makes about 1,000 horsepower naturally. At 20,000 feet, without the turbosupercharger, it would make perhaps 600 horsepower. But with the turbosupercharger maintaining sea-level manifold pressure, it still makes 1,000 horsepower. Or more. The implications were staggering. "This means the P-38 has no combat ceiling limit in any practical sense," another engineer said slowly. "It can fight effectively at altitudes where our fighters are struggling for basic power." Over the next several days, the Japanese engineering team disassembled one of the Allison engines to study the turbosupercharger system in detail. What they found was both impressive and depressing. The General Electric turbosupercharger was a masterpiece of engineering. The turbine wheel, spinning at incredible speeds in a stream of exhaust gases exceeding 700 degrees Celsius, was made from exotic high-temperature alloys. The compressor side featured precision-machined impeller blades designed to maximize air compression efficiency. The entire system was controlled by an automatic regulator that maintained optimal manifold pressure regardless of altitude. Pilots didn't need to manually adjust settings constantly. The system managed itself. Japanese engineers examined the metallurgy of the turbine wheel. They tested the alloys. They studied the manufacturing techniques visible in the components. Their conclusion was sobering. Japan could not replicate this technology. "We lack the high-temperature alloys," one metallurgist reported. "The turbine operates in conditions that would destroy any materials we can currently produce. The exhaust gases are too hot. The rotational speeds are too high. We don't have alloys that can survive these conditions for more than a few hours before failing." Even if they had the materials, the manufacturing was beyond Japanese capabilities. The turbine wheels required precision machining and balancing that Japanese facilities couldn't achieve at scale. These were not components that could be hand-crafted by skilled workers. They required advanced machine tools and manufacturing processes. "The Americans have industrialized sophisticated technology," the lead engineer observed grimly. "They're not just designing advanced systems. They're manufacturing them in quantity. This P-38 is one of thousands. Every single one has 2 of these turbosuperchargers. That means they're producing these complex, high-precision components at a rate of thousands per month. The Japanese team also studied the intercooler system. After the turbosupercharger compressed the air, it became hot. Hot air is less dense, which reduces the benefit of compression. So the P-38 routed the compressed air through intercoolers mounted in the wing leading edges, where ram air cooled it back down before it entered the engine. More complexity. More weight. More systems to maintain. But also, significantly more power at altitude. The comparison to Japanese engines was humbling. Japan's best fighter engine, the Nakajima Sakare radial used in the Zero, produced about 1,050 horsepower at sea level using a 2-speed mechanical supercharger. At 20,000 feet, it produced perhaps 600 horsepower. The P-38's twin Allisons produced over 1,000 horsepower each at sea level. At 20,000 feet, they still produced nearly 1,000 horsepower each. 2,000 horsepower total, compared to the Zero's 600.at altitude, the P-38 had more than 3 times the power available. This explains everything we've observed in combat, the lead evaluation pilot said, reviewing the data. When P-38s climb away from us, it's not pilot skill. It's raw power advantage. When they dive away and we cannot catch them, it's because they have the power to pull away even in a dive. Lieutenant Nishizawa, who had also flown the captured P-38, added his observations. The engines are smooth. Very little vibration. The power delivery is linear and predictable. In the Zero, you learn to work with the engine's characteristics. In the P-38, the engines just do what you ask them to do. The liquid cooling system also impressed the Japanese engineers. The Allison V-1710s used a pressurized ethylene glycol cooling system with radiators mounted in the center wing section. Japanese fighters overwhelmingly used air-cooled radial engines. These were simpler and lighter, but they created significant drag and were vulnerable to combat damage. One bullet through a cylinder could disable an engine. The P-38's liquid-cooled engines were more complex, but they offered advantages. The streamlined cowlings reduced drag. The cooling system could maintain precise temperatures for optimal performance. And the engines could survive certain types of damage that would destroy an air-cooled radial. A small coolant leak is not immediately fatal, one engineer noted. The engine can run for some time with reduced coolant. But a cylinder damage on our radials means immediate and catastrophic power loss. The Japanese team also discovered self-sealing fuel tanks, armor plating behind the pilot seat, and redundant systems throughout the aircraft. The P-38 was designed to bring pilots home even after taking damage. Japanese fighters sacrificed all of this for weight savings and performance. A Zero had no armor, no self-sealing tanks, no redundant systems. One good burst could set it ablaze. But the turbo-supercharger system remained the most significant discovery. It represented a fundamental technology gap that Japan had no immediate way to close. The lead engineer wrote in his evaluation report, "The turbo-supercharger gives American fighters a decisive advantage at altitudes above 15,000 feet. Our fighters cannot compete in this regime. We can either avoid combat at these altitudes or accept heavy losses. Without equivalent technology, we cannot match P-38 performance." He added a recommendation that would go nowhere: Japan must prioritize development of turbo-supercharger technology. This will require investment in metallurgy research, precision manufacturing capabilities, and extensive testing. Estimated timeline, 3 to 5 years minimum. By 1943, Japan didn't have 3 to 5 years. The industrial and technological race was already lost. They just hadn't fully accepted it yet. The lead ace flew the P-38 several more times, each flight revealing new aspects of its capabilities. On one flight, he climbed to 30,000 feet, an altitude where the Zero would be nearly helpless, struggling for every foot of altitude, controls mushy, engine gasping for oxygen. The P-38 climbed to 30,000 feet and still had performance in reserve. The pilot could have climbed higher if needed. The engines purred smoothly, delivering steady power. The controls remained responsive. The aircraft was comfortable at altitudes that would be desperate struggles in Japanese fighters. He descended in a high-speed dive, something P-38 pilots regularly did to escape Japanese fighters. He pushed the nose over and let the P-38 accelerate. The airspeed indicator climbed past 400 miles per hour. 420. 440. The aircraft remained stable and controllable. In a zero, this would be approaching structural limits. The airframe would be shaking. The controls would be stiffening. Pulling out of such a dive would risk structural failure. The P-38 handled it effortlessly. The pilot pulled back on the yoke at over 450 miles per hour, and the aircraft came out of the dive smoothly, without buffeting or structural complaints. "We have been fighting an aircraft we fundamentally misunderstood," the lead ace told the engineering team after that flight. "We thought the P-38 was just a heavy, clumsy fighter that relied on speed. But it's not clumsy. It's powerful. There's a difference. Clumsy means poor design. Powerful means capability that comes from superior technology." The turbosupercharger revelation forced Japanese commanders to reconsider their tactical assumptions. If American fighters could dominate at high altitude, Japanese fighters would need to force combat at lower altitudes where the turbosupercharger advantage was minimized. But that gave Americans the initiative. They could choose whether to accept combat or not. They could fight at the altitude of their choosing. And increasingly, they chose to fight at 20,000 feet or higher, where their technology gave them overwhelming advantage. The captured P-38's engines told a story that extended far beyond aviation technology. They revealed an industrial and scientific capability that Japan could not match. The turbosuperchargers alone required advanced metallurgy, precision manufacturing, sophisticated controls, and mass production capabilities that represented years of development and billions of yen in industrial infrastructure. America had all of this. Japan did not. And the gap was widening every month. The engines were eventually removed from the captured P-38 and sent to Japan for further study. Japanese engineers would examine them for years, hoping to learn something that could be applied to their own designs. But copying advanced technology is not the same as understanding the industrial base that produces it. Japan could study the turbosuperchargers. They could even, perhaps, build a few prototype copies. But they could never manufacture them at the scale and cost that made them practical for American fighters. The fork-tailed devil's power came not just from clever engineering, but from an industrial system that could turn advanced technology into mass-produced reality. And that was a lesson the Japanese engineers understood perfectly, even if their commanders didn't want to hear it. After his initial familiarization flights, the lead evaluation pilot was ready for the real test. Pushing the P-38 to its limits in simulated combat conditions. On June 8, 1943, the ace took off from Rabaul with a specific mission: fly the P-38 as aggressively as American pilots flew it in combat. No gentle exploration. No cautious testing. He would throw the aircraft around the sky and see what happened. Lieutenant Nishizawa would fly chase in a zero, both to observe the P-38's performance and to provide comparison data. A second Zero would fly high cover to warn of any actual Allied aircraft in the area. The last thing they needed was to have their captured P-38 shot down by the Allies. The lead pilot climbed to 15,000 feet and leveled off. He checked the engine instruments. Both Allisons running smoothly. Oil pressure and temperature normal. Fuel state good. Everything ready. He radioed Nishizawa. Beginning performance tests now. Stay clear until I call you in. First test, maximum level speed. The ace pushed both throttles to the firewall and activated the war emergency power setting. The P-38 surged forward. He held it level, letting the airspeed build. The ASI needle climbed steadily. 300 miles per hour. 320. 3-40. In A0. Maximum speed at this altitude was around 330 miles per hour. The P-38 blew past that without effort. 360. 380. 400 miles per hour. The airspeed was still increasing. The pilot felt the controls grow heavier as dynamic pressure built up, but the aircraft remained stable. No buffeting. No vibration. Just smooth, powerful acceleration. 410. 415. 420 miles per hour. Finally, the acceleration slowed. The P-38 had reached its maximum level speed at 15,000 feet, approximately 425 miles per hour. The ace eased back the throttles and let the aircraft slow down. He was shaking slightly, and not from the flight. That speed run had been a revelation. The P-38 was 90 to 100 miles per hour faster than a Zero at the same altitude. 90 miles per hour. That wasn't a small advantage. That was a different category of performance entirely. He radioed Nishizawa. "Join up on me. Let's test relative performance." Nishizawa's Zero pulled alongside. The two aircraft flew in formation, providing a stark visual contrast. The Zero looked delicate, almost fragile next to the P-38's bulk. But appearances were deceiving. The question was, which philosophy worked better in combat? "Let's test acceleration," the lead pilot called. "Both of us will be flying at 250 miles per hour. On my mark, we both go to full power and see who accelerates faster." They set up, both aircraft flying straight and level at 250 miles per hour. 3, 2, 1, mark. Both pilots slammed throttles forward. The ace in the P-38, Nishizawa in the Zero. Initially, the Zero jumped ahead slightly. Its lighter weight gave it better initial acceleration. But within seconds, the P-38's raw power advantage began to tell. The ace felt himself being pushed back in the seat as 2,000 horsepower drove the aircraft forward. The P-38 caught up to the Zero, then pulled ahead. And kept pulling ahead. After 30 seconds, there was a significant gap. After a minute, the Zero was falling behind rapidly. "You're walking away from me," Nishizawa reported, frustration evident in his voice. "I'm at full power and you're just disappearing ahead." The lead pilot eased back and let Nishizawa catch up. The lesson was clear. In any extended speed run, the P-38 would win. A Zero pilot who tried to chase a P-38 in level flight was wasting fuel and time. The P-38 would simply pull away. Next test, zoom climb. This was a tactic American P-38 pilots used constantly. Build speed, then convert that speed into a rapid climb, gaining altitude faster than pursuing Japanese fighters could follow. The ace of the P-38 to build speed, accelerating to over 400 miles per hour. Then he pulled back hard on the yoke, converting all that velocity into vertical climb. The P-38 went nearly vertical. The G-forces pressed the pilot into his seat. The airspeed bled off rapidly, but the altitude climbed at an incredible rate. 4,000 feet per minute. 5,000. 6,000 feet per minute. In seconds, the ace had gained 3,000 feet of altitude. He rolled the aircraft over the top of the zoom climb and looked down. Nishizawa's Zero was thousands of feet below, unable to follow. "I can't match that climb rate," Nishizawa reported. "You're gone. If this were real combat, I'd have lost you." The evaluation pilot understood now why American P-38 pilots could engage Japanese fighters at will and disengage whenever they chose. The speed and climb performance gave them complete control of the engagement. They could fight when they had an advantage and simply climb away when they didn't. Japanese fighters couldn't force combat on unwilling P-38 pilots. And that was a devastating tactical reality. Next came dive tests. This was another area where P-38 pilots had a reputation for being untouchable. Japanese pilots reported that P-38s could dive away from any pursuit and simply disappear. The lead pilot rolled the P-38 inverted and pulled through into a vertical dive. Gravity and power combined to accelerate the aircraft rapidly. The airspeed climbed alarmingly fast. 350. 400. 450 miles per hour. The controls grew very heavy. The yoke required significant force to move. But the aircraft remained stable. No flutter. No buffeting. The P-38 structure was massively strong, designed to handle these speeds. At 475 miles per hour, the pilot began the recovery. He pulled back hard on the yoke, using both hands and significant arm strength. The G-forces built up. His vision began to gray at the edges. The G-suit he was wearing helped, but it was still brutal. The P-38 came out of the dive smoothly, transitioning from vertical to level flight in a sweeping arc. The ace checked his altitude. He had started the dive at 15,000 feet and recovered at 8,000 feet. 7,000 feet of altitude converted to speed in seconds. He radioed Nishizawa. "Follow me down in a dive. Stay with me if you can." They set up again. On the lead pilot's mark, both aircraft rolled into steep dives. Initially, Nishizawa's lighter Zero accelerated quickly. But as the speeds increased past 350 miles per hour, things changed. The P-38 continued accelerating smoothly. The Zero's acceleration began to slow as drag increased. At 400 miles per hour, the P-38 was pulling away from the Zero. At 420, the gap was substantial. Nishizawa reported that his controls were becoming very heavy and he was concerned about structural limits. Breaking off, Nishizawa called. "I can't follow you any deeper." The ace continued the dive alone, pushing the P-38 to 480 miles per hour before pulling out. The conclusion was inescapable. A P-38 that wanted to escape combat could simply dive away, and no Japanese fighter could follow. The Americans had a built-in escape option that made their pilots much safer. But what about dogfighting? The P-38 was fast and powerful, but could it turn with Japanese fighters? The lead pilot called Nishizawa for the test everyone was most curious about. "Let's dogfight. You try to get on my tail. I'll try to get on yours. Let's see what happens." They set up at 10,000 feet, about 1 kilometer apart. On the lead pilot's mark, they turned toward each other. Nishizawa's Zero turned hard, its legendary maneuverability on full display. The Zero could turn inside almost any fighter in the world. Japanese pilots had built their entire tactical doctrine around this advantage. The ace turned the P-38 as hard as he dared. The aircraft responded, banking steeply, but it didn't turn as tightly as the Zero. Not even close. Nishizawa was turning inside him, beginning to gain position. In a sustained, slow-speed turning fight, the Zero was clearly superior. This confirmed what everyone already believed. But the lead pilot had read American tactical reports that Japanese intelligence had captured. American pilots didn't fight this way. They didn't try to outturn Japanese fighters. They used different tactics. The ace broke off the turn and extended away, using the P-38's speed advantage. He accelerated to 350 miles per hour, opening distance from Nishizawa's Zero. Then he used that speed to zoom climb, gaining altitude. He came back around with an energy advantage. More speed and more altitude than Nishizawa. He dove on the Zero, making a high-speed slashing attack. Nishizawa turned hard to evade, but the ace wasn't trying to follow him through the turn. He fired a brief simulated burst as he passed at high speed, then used his momentum to climb back to altitude. "Hit," the lead pilot called. In a real fight, that burst would have damaged you. They reset and tried again. And again. Each time, the ace used speed and altitude advantage to make hit-and-run attacks. Nishizawa's superior turning ability couldn't help him because the P-38 pilot never stayed in the turn. He slashed through, attacked, and climbed away before Nishizawa could bring his guns to bear. After several iterations, Nishizawa was frustrated. "I can't catch you when you don't stay and fight. You're faster, so you control the engagement." "Exactly," the lead pilot replied. "American pilots don't fight the way we do. They don't try to turn with us. They use their speed and power to control the fight. And we can't force them to fight on our terms." They landed back at Rabaul, both pilots shaken by what they had learned. The ground crew and engineers crowded around, eager for reports. The ace climbed out of the P-38 slowly, his flight suit soaked with sweat. Flying the P-38 aggressively was physically demanding in ways that flying a Zero wasn't. The controls were heavier. The G-forces were higher because the aircraft could pull harder. Everything about it required more strength and stamina, but the performance was undeniable. The P-38 is not superior to the Zero in turning, the lead pilot reported to the assembled officers and engineers. In a slow-speed dogfight, the Zero wins every time. But the Americans don't fight that way. They use their speed and power to control the engagement. They attack when they have advantage and disengage when they don't. And we cannot stop them from doing this. He pointed at the P-38. This aircraft can outrun us in level flight. It can outclimb us at any altitude. It can outdive us by a huge margin. The only thing we do better is turn. And that one advantage is not enough when the enemy can choose whether to engage our turn or not. Lieutenant Nishizawa added his perspective. In the Zero, I always felt I had a chance. If I could get an American into a turning fight, I would win. But after today, I understand that skilled P-38 pilots will never give me that opportunity. They will fight on their terms, not mine. An intelligence officer asked the critical question. Can our pilots develop tactics to counter the P-38? The lead pilot thought carefully before answering. Yes and no. We can minimize the P-38's advantages by forcing combat at lower altitudes where the turbosupercharger benefit is reduced. We can try to ambush them when they're slow, during takeoff or landing. We can use clouds and weather to close distance before they see us. He paused. But fundamentally, the P-38 pilot has the initiative. He chooses whether to fight or not. If he wants to escape, he can. If he wants to attack, he has the speed and power to do it on his terms. We are reacting to his choices, not making our own. The assembled officers digested this sobering assessment. One asked, what about numbers? If we have numerical superiority, can we overwhelm P-38 formations? Perhaps, the ace said. But that assumes we can maintain numerical superiority. And the reports I've seen suggest the Americans are producing P-38s far faster than we are producing Zeros. The numbers advantage may not be ours for much longer. That evening, the lead pilot wrote his official flight test report. His conclusions were blunt. The P-38 Lightning represents a paradigm shift in fighter design and tactics. It sacrifices turn performance for speed, power, and altitude capability. In the hands of a well-trained pilot who understands energy fighting tactics, it is extremely difficult to counter with current Japanese fighters. He added recommendations that would prove prophetic. Japanese pilots must receive training in energy management and tactics suitable for fighting faster, more powerful opponents. Our doctrine emphasizes turning combat because that is where our fighters excel. But this doctrine is obsolete against aircraft like the P-38. We must adapt or face increasingly heavy losses. The speed tests had revealed an uncomfortable truth. Japan was fighting a technological and tactical battle it was not prepared for. The P-38 wasn't just a better fighter. It was a different kind of fighter, built around a different philosophy of air combat. And that philosophy was winning. After thoroughly evaluating the P-38's engines and high-altitude performance, the Japanese test team moved on to what they considered the most critical question. How did the P-38 handle in a dogfight? Japanese fighter doctrine was built entirely around close-range maneuvering combat. The Zero had been designed specifically to outturn any opponent. Japanese pilots trained relentlessly in aerobatic maneuvers and tight turning engagements. Victory in aerial combat, according to Japanese thinking, came from superior maneuverability, so the question burning in every pilot's mind was simple. Could the P-38 turn with a Zero? Lieutenant Nishizawa volunteered to fly the captured P-38 against a Zero flown by another experienced pilot in mock combat. This would be the ultimate test. Japanese against American design philosophy, played out in the skies over Rabaul. The morning of the test dawned clear and hot. Perfect conditions. Nishizawa climbed into the P-38 while his opponent, Lieutenant Sasai, strapped into a Zero that had been brought to Rabaul specifically for comparison testing. The rules were simple. Both aircraft would start at 10,000 feet, a mile apart. On radio signal, they would engage in mock combat. No live ammunition, but both pilots would call out when they achieved a firing position on the other. Observing pilots and engineers crowded onto the airfield and nearby hills, watching through binoculars. This was the moment many had been waiting for. The radio crackled. Begin. Sasai and the Zero immediately turned hard toward the P-38, pulling into a tight climbing turn. This was standard Zero tactics: turn into the enemy, gain position, exploit superior maneuverability to get on their tail. Nishizawa in the P-38 did something different. He didn't turn to meet the Zero. Instead, he pushed the throttles forward and climbed away, using the P-38's superior power and climb rate to gain altitude advantage. Sasai tried to follow, pulling the Zero's nose up, but the P-38 climbed away effortlessly. Within 30 seconds, Nishizawa had a 1,000-foot altitude advantage. Then he rolled inverted and came down on the Zero from above. Sasai saw him coming and turned hard, trying to force an overshoot. The Zero could turn inside any aircraft. If he could get the P-38 to try turning with him, Sasai would win easily. But Nishizawa didn't try to turn with the Zero. He dove past at high speed, called out, "Guns, guns, guns," to indicate he had a firing solution, then zoomed back up using his excess speed to regain altitude. The watching pilots understood immediately. The P-38 wasn't fighting a turning battle. It was fighting an energy battle. For the next 10 minutes, the mock combat continued. Every time Sasai tried to turn into Nishizawa, the P-38 simply used its power and speed to disengage, reposition, and attack from a position of advantage. The Zero could turn tighter, but it could never force the P-38 into a turning fight. When both aircraft landed, Sasai climbed out of his Zero frustrated. "I couldn't catch him. Every time I thought I had position, he just powered away. The speed difference is too great." Nishizawa was equally emphatic. "I never felt threatened. As long as I didn't try to turn with him, I could control the entire engagement. I chose when to attack and when to disengage. He had no choice but to react." The test was repeated with different pilots, different starting conditions, and different altitudes. The results were always the same. In a pure turning fight, the Zero was superior. But the P-38 didn't need to turn with the Zero. It fought on its own terms. The lead evaluation pilot analyzed the results carefully. This explains why P-38s have been so difficult to shoot down. They're not trying to dogfight us. They use speed and altitude advantage to dictate the terms of engagement. If they have the advantage, they attack. If they don't, they disengage. And we cannot catch them when they choose to leave. The Japanese engineers set up formal maneuverability tests to quantify the differences. They measured turn radius, turn rate, roll rate, and other handling characteristics. The Zero could complete a 360-degree turn in approximately 16 seconds at optimal speed. The P-38 required about 22 seconds. Clear advantage to the Zero in sustained turning. But other measurements told a different story. The P-38's roll rate was actually superior to the Zero. The long wings and heavy ailerons of the Zero made it relatively slow to roll into a turn. The P-38, with its boosted ailerons and shorter effective wingspan due to the twin-boom design, could roll quickly despite its weight. This meant the P-38 could change direction faster, even if it couldn't sustain as tight a turn. In combat, the ability to quickly roll into a dive or reverse direction was often more valuable than pure turning ability. The P-38's stall characteristics were also benign. The Zero would snap viciously if stalled in a turn, flicking into a spin that required altitude and skill to recover. The P-38 simply buffeted and mushed when stalled, giving clear warning and remaining controllable. The Zero punishes pilot error harshly, noted one test pilot. The P-38 forgives mistakes. This makes it safer for average pilots. High-speed handling was where the P-38 truly excelled. At speeds above 300 miles per hour, the Zero's controls became heavy and unresponsive. The aircraft was designed for combat at 200 to 250 miles per hour, where its legendary maneuverability was most effective. The P-38 remained fully controllable at speeds exceeding 400 miles per hour. At these speeds, the Zero couldn't compete at all. Nishizawa conducted a test that dramatically illustrated this point. He accelerated the P-38 to 400 miles per hour in level flight, then executed a series of rolling maneuvers and direction changes. The aircraft responded crisply to all control inputs. Then Sasai attempted the same in the Zero. At 400 miles per hour, the Zero's controls were so heavy that the pilot could barely move them. Attempting a roll took tremendous physical effort and produced sluggish results. The Zero was essentially helpless at these speeds. This is why diving away works so well for P-38 pilots, the lead ace observed. Once they exceed 350 miles per hour, we cannot follow effectively. Our controls are too heavy. The aircraft doesn't respond properly. We either give up the chase or risk losing control. The vertical performance difference was even more pronounced. The P-38 could enter a zoom climb from level flight and gain several thousand feet while maintaining control and energy. The Zero attempting the same maneuver would run out of energy much more quickly. They fight in the vertical plane, Nishizawa explained to the assembled pilots. We fight in the horizontal plane. They use altitude and speed. We use turning and positioning. These are fundamentally different combat styles. The question became, which style was more effective? In early war engagements over China and in the first months after Pearl Harbor, Japanese turning tactics had been devastatingly effective. Allied pilots tried to dogfight Zeros and died in large numbers. The Zero's superior maneuverability, combined with experienced Japanese pilots, created a myth of invincibility. But by 1943, American pilots had learned not to dogfight. They used tactics developed by pilots like John Thatch and Tommy Maguire: maintain speed, use altitude advantage, attack from above, and never try to turn with a Zero. The P-38 was perfectly suited to these tactics. It could execute boom and zoom attacks that played to its strengths while avoiding situations that played to Japanese strengths. One test was particularly revealing. Nishizawa flew the P-38 while 3 Zeros attempted to intercept him using standard Japanese tactics. The scenario was simple. Nishizawa would try to escape, the Zeros would try to shoot him down. Nishizawa climbed to 20,000 feet, then the engagement began. The 3 Zeros climbed after him, but their rate of climb was inferior. By the time they reached 18,000 feet, Nishizawa was at 25,000 feet. He dove on them at high speed, made a single firing pass, then zoomed back to altitude using his excess speed. The Zeros scattered and tried to reform, but before they could organize, Nishizawa was diving on them again from a different angle. This continued for 15 minutes. The P-38 made repeated attacks, then disengaged before the Zeros could respond effectively. The 3 Japanese fighters could never coordinate an effective counter because they couldn't predict where the P-38 would attack from next. When the exercise ended, all 3 Zero pilots reported the same thing: frustration and helplessness. They could see the P-38. They knew where it was. But they couldn't catch it, couldn't force it into a turning fight, couldn't do anything except try to evade its attacks. This is what our pilots face in actual combat, one of the Zero pilots said soberly. We're fighting an enemy who refuses to fight our way. And we have no answer. The Japanese engineers documented another crucial factor: pilot fatigue. The P-38 was physically easier to fly than the Zero. Its hydraulically boosted controls required less physical effort. Its stable handling meant pilots didn't need to constantly fight the aircraft. In extended combat, this mattered enormously. A Zero pilot would be physically exhausted after 30 minutes of hard maneuvering. Pulling sustained high G turns in the lightweight fighter required tremendous physical effort and endurance. P-38 pilot could fight for an hour and still be relatively fresh. The aircraft did more of the work. The boosted controls reduced physical strain. The stable platform meant less constant correction. In a long engagement, the P-38 pilot has an advantage simply from reduced fatigue, noted one Japanese flight surgeon who observed the tests. Our pilots are elite athletes, but even they tire. The Americans have built an aircraft that doesn't demand as much from its pilot physically. The counter-rotating propellers also provided an unexpected advantage in combat maneuvering. The Zero had strong torque effects that required constant rudder input, especially during hard turns or at high angles of attack. Pilots learned to compensate automatically, but it required attention and control deflection. The P-38's counter-rotating props eliminated this entirely. The aircraft flew straight without compensation. This meant pilots could focus entirely on tactics and targeting rather than fighting the aircraft's handling quirks. After 2 weeks of intensive maneuverability testing, the conclusions were clear and somewhat paradoxical. The Zero was more maneuverable in traditional dogfighting metrics. It could outturn the P-38 easily. In a slow-speed, turning engagement, the Zero had decisive advantages. But the P-38 could avoid slow-speed turning engagements entirely. It could fight at speeds and altitudes where the Zero's advantages disappeared. It could attack and disengage at will. The question wasn't which aircraft was more maneuverable. The question was which combat style was more effective in modern aerial warfare. The lead evaluation pilot wrote in his evaluation report, "The P-38 represents a new philosophy of fighter combat. It uses energy management rather than instantaneous maneuverability. It maintains speed and altitude advantage rather than seeking close-range dogfights. Against opponents who understand and apply these tactics, our maneuverability advantage becomes irrelevant." He concluded with a recommendation that would be largely ignored: we must develop new tactics and new aircraft to counter the American approach. Our current methods, built around low-speed maneuverability, are becoming obsolete. We are training pilots for the wrong kind of air war. The fork-tailed devil didn't outturn the Zero. It didn't need to. It had changed the rules of engagement entirely. And that was more dangerous than any amount of maneuverability could have been. On the 5th day of evaluation, the Japanese team turned their attention to what many pilots considered the P-38's most fearsome characteristic: its armament. The Lightning carried its weapons in the nose, clustered tightly around the cockpit. 4 Browning M250 caliber machine guns and 1 Hispano-Suiza 20mm cannon. All 5 weapons pointed straight ahead, firing along the aircraft's centerline. To pilots accustomed to wing-mounted guns, this arrangement seemed almost wasteful. Why concentrate everything in the nose when you could spread weapons across the wings for more total firepower? But as the Japanese engineers examined the system, they began to understand the brilliance of the design. The lead ace had experienced P-38 firepower from the receiving end. He had watched the aircraft's nose light up with muzzle flashes, then seen Zeros and Bettys disintegrate under concentrated fire. Now he wanted to understand exactly why nose-mounted guns were so devastating. The engineering team set up the captured P-38 for gunnery demonstrations. They loaded practice ammunition and set up target panels at various ranges on the beach near Rabaul. First, they examined the gun installation itself. All 5 weapons were mounted in the nose section, stacked vertically. The 450 caliber guns were positioned 2 above and 2 below the 20mm cannon, which occupied the central position. "Notice the mounting arrangement," one engineer pointed out. "The guns are fixed rigidly to the airframe structure. No flexible mounts. No adjustment mechanisms. They're aimed precisely along the aircraft's longitudinal axis and locked in place." This was completely different from Japanese practice. Zero fighters mounted their weapons in the wings, typically 2 20mm cannons in the outer wing panels and 2 7.7mm machine guns in the fuselage. Wing-mounted guns required convergence adjustment, setting them to aim at a specific point ahead of the aircraft where all the bullets would cross paths. "What convergence distance did American pilots use?" asked one of the Japanese pilots. An intelligence officer consulted captured documents. "Typically 300 yards, or approximately 270 meters. But here's the important point: with nose-mounted guns, convergence is not really a factor. The guns all fire parallel to each other along the centerline. They don't converge at a specific distance. They create a cone of fire that simply expands slightly with range." The implications took a moment to sink in. "So a P-38 pilot has the same aiming point at any range?" the lead ace asked. "Exactly. Whether the target is 100 meters away or 400 meters away, the pilot aims the same way. The bullet stream doesn't shift. It just expands slightly." The Japanese pilots exchanged looks. This was a significant advantage they hadn't fully appreciated before. In A0, pilots had to estimate range constantly because the gun convergence point was fixed. Too close or too far from the optimal convergence distance, and the bullets from the wing-mounted cannons would pass on either side of the target rather than hitting it. Pilots learned to compensate through experience, but it required judgment and introduced uncertainty. The P-38 eliminated this problem entirely. The pilot simply put the gun sight on the target and fired. At any range within the gun's effective envelope, the bullets went where the sight was aimed. The test team conducted firing demonstrations to visualize this difference. They set up target panels at 100, 200, and 300 meters. When they fired the P-38's guns, the bullet patterns at all three ranges showed the same point of impact, just with increasing spread as distance increased. A pilot aiming at the center of an aircraft would hit the center of that aircraft regardless of range. This explains the reports of P-38s achieving kills with very short bursts, Nishizawa observed. They don't need to walk their fire onto the target or compensate for convergence. First-round hits are much more likely. The concentration of firepower was even more impressive when they examined the actual destructive power. 450 caliber machine guns firing together delivered approximately 60 rounds per second of heavy machine gun fire. Each bullet carried tremendous kinetic energy and could penetrate engine blocks, cut through structural members, and destroy control systems. The 20mm cannon added explosive rounds that could tear apart aircraft structures with each hit. The cannon fired at approximately 10 rounds per second, interspersed with the machine gun fire. Together, the 5 weapons created a destructive stream of fire that was unmatched by any Japanese fighter. The Zero's armament consisted of two 20mm cannons with 60 rounds each and two 7.7mm machine guns with 500 rounds each. The cannons were powerful but had limited ammunition. The machine guns had plenty of ammunition but lacked hitting power against aircraft with any armor protection. Pilots had to choose: use the powerful but limited cannons, or spray with the weaker machine guns that had more ammunition. It was a constant compromise. The P-38 had no such compromise. The 450 caliber guns carried 500 rounds each, giving 2,000 rounds total. The 20mm cannon had 150 rounds. This meant sustained firing capability that Japanese pilots could only dream of. A P-38 pilot can fire for approximately 15 seconds continuously before exhausting ammunition, an engineer calculated. Our Zero pilots run out of cannon ammunition in about 5 seconds of continuous fire. Then they're left with only the light machine guns. The lead pilot thought about this in terms of combat reality. Most firing opportunities in combat last only 1 or 2 seconds. Maybe 3 seconds if you have a good setup. The P-38 has enough ammunition for 7 or 8 separate firing passes. A Zero pilot might get 3 cannon passes before running dry. The harmonization of the weapons was another revelation. In the P-38, all 5 guns were bore-sighted to converge slightly at 300 yards, but because they were so close together physically, they essentially created a single point of impact. The Japanese engineers measured the weapon spacing. The guns were clustered in a space less than 1 meter wide and 70 centimeters tall. At typical combat ranges of 2 to 300 meters, this tight grouping meant that essentially all the firepower hit the same point on the target aircraft. It's like being hit by a single, massive weapon rather than 5 individual guns, one engineer noted. The destructive effect is concentrated on a small area, causing catastrophic damage rather than scattered hits. They conducted a demonstration that viscerally illustrated this point. They set up a Zero wing panel as a target at 200 meters and fired a 1-second burst from the P-38. The wing panel was utterly destroyed. The concentrated fire from 450 caliber guns and the 20mm cannon had literally torn a meter-wide hole through the aluminum structure. The panel was unrecognizable as an aircraft component. The watching pilots were silent. This was what P-38 fire did to Japanese aircraft. One good burst and the target was destroyed, not damaged but destroyed. "We've seen this in combat," one pilot finally said. "I watched a P-38 fire a very short burst at a Betty bomber. The Betty came apart in midair. I thought at the time it had been a lucky hit to a fuel tank or bomb load. Now I understand it was just the normal effect of concentrated firepower." The fire control system also impressed the Japanese evaluators. The P-38 used a gyroscopic gun sight that helped pilots aim at maneuvering targets. The sight automatically computed the correct lead angle for deflection shots. A pilot simply put the sight's pipper on the target, matched the target's wingspan to a reference circle in the sight, and the gyroscopic mechanism calculated the proper lead. It wasn't perfect, but it gave even average pilots a much better chance of hitting with deflection shots. Japanese fighters used simple fixed gun sights. A pilot had to manually estimate lead based on experience and intuition. Novice pilots struggled with this for months. Even experienced pilots missed far more often than they hit when attempting high deflection shots. This sight system lowers the skill floor dramatically, the lead ace observed. An average American pilot with this gun sight can achieve hits that would require exceptional skill in our aircraft. They've automated part of the aiming process. The maintenance and reliability of the weapon system was equally noteworthy. The Japanese engineers examined the gun mounts, feed systems, and electrical firing mechanisms. Everything was designed for reliability and ease of maintenance. The guns were mounted on quick-release mounts that allowed armament crews to remove and replace a gun in minutes. The ammunition feed systems were robust and jam-resistant. The electrical firing system had redundant circuits. In our fighters, a gun jam requires the pilot to manually clear it in flight, which is often impossible in combat, one pilot noted. The P-38 has spent casings ejected automatically, and the gun mechanisms are designed to minimize jamming. If a gun does jam, the pilot still has 4 other weapons. The ammunition storage was also cleverly designed. The 50 caliber ammunition boxes were located in the nose, close to the guns, minimizing feed distance and reducing jam potential. The 20 mm ammunition drum was positioned directly behind the cannon. Japanese wing-mounted cannons required long, complex feed mechanisms from ammunition boxes in the wing roots out to the guns in the outer wing panels. These systems were prone to jamming, especially during high-G maneuvers when ammunition belts could bind or skip. The psychological impact of the P-38's firepower came up repeatedly in discussions with pilots who had faced it in combat. When you see a P-38 lining up on you, you know you have perhaps 1 second to evade before devastating fire arrives, one pilot explained. There's no gradual build-up of hits. It's instant, catastrophic destruction if the pilot's aim is true. This creates tremendous pressure to break off engagements early, which gives the P-38 pilot tactical advantage. Another pilot added, "In our fighters, we often damage enemy aircraft without destroying them. We score hits, force them to withdraw, but they make it back to base. The P-38 doesn't damage. It destroys." Aircraft hit by P-38 fire are usually total losses, not just damaged. The evaluation team also examined gun camera footage that had been recovered from other captured P-38s and from Japanese intelligence sources. The footage showed P-38s engaging Japanese aircraft, and the results were consistent and shocking. Typical engagement: P-38 approaches from above or behind. Brief firing pass, usually 1 to 2 seconds. Target aircraft explodes, catches fire, or breaks apart. P-38 continues past and climbs away. The concentration of firepower meant that even brief firing opportunities resulted in kills. P-38 pilots didn't need prolonged tracking time. A snapshot was often enough. "Compare this to our combat footage," an intelligence officer noted. "Our pilots often fire for 3, 4, 5 seconds at a target, scoring multiple hits but not achieving kills. The enemy aircraft returns to base damaged. The P-38 achieves kills with 1-second bursts." The ammunition types also differed significantly. American 50 caliber ammunition included armor-piercing, incendiary, and tracer rounds mixed in the belts. This combination could penetrate armor, start fires, and provide aiming reference. Japanese 20 mm cannon ammunition was powerful but less versatile. The high-explosive rounds were devastating when they hit, but the limited ammunition capacity meant pilots had to be selective about when to fire. The lead evaluation pilot summarized the firepower evaluation in stark terms. The P-38's armament system represents a complete weapons platform optimization. Everything from gun placement to ammunition capacity to fire control is designed for maximum effectiveness. A pilot of average skill can achieve kills that would require exceptional marksmanship in our fighters. He added a sobering observation: when I fought P-38s in my Zero, I always knew that if a P-38 got a clean firing solution on me, I would likely not survive. The firepower was overwhelming. This knowledge affected every tactical decision. I had to avoid giving them any opportunity to fire, which meant I was always defensive, always reacting. The psychological advantage this gave P-38 pilots cannot be overstated. The engineering team concluded their firepower evaluation with a simple but profound statement in their report: the P-38's nose-mounted armament is not simply a different design choice. It is a force multiplier that gives American pilots a significant combat advantage. We have no equivalent capability in our current fighter inventory, and developing one would require fundamental redesign of our aircraft. The fork-tailed devil didn't just carry guns. It carried a precision weapon system that turned average pilots into deadly marksmen and good pilots into unstoppable aces. And the Japanese had no answer for it. On the 10th day of evaluation, the Japanese engineering team focused on one of the P-38's most strategically significant capabilities: its extraordinary range. Range was supposed to be Japan's advantage. The Zero had been designed specifically for long-range operations over the vast Pacific. It could fly over 1,600 miles with drop tanks, allowing Japanese fighters to escort bombers on missions that seemed impossible to the Allies in the early war years. Japanese pilots took pride in this capability. They had flown from Rabaul to Guadalcanal and back, a round trip of over 1,100 miles, regularly throughout 1942 and early 1943. This feat of endurance gave Japan tactical flexibility that seemed unmatched. But now, examining the captured P-38, the Japanese team discovered something that shook this assumption. The Lightning could match or exceed the Zero's range while carrying heavier armament, armor protection, and far more powerful engines. The lead engineer led the range analysis. He began by mapping out the P-38's fuel system, which proved to be remarkably sophisticated. The aircraft had multiple internal fuel tanks. Two main tanks in the center wing section held a total of 410 gallons. Two reserve tanks in the inner wings added another 120 gallons. And two additional tanks in the leading edge of the outer wings held another 60 gallons. Total internal fuel capacity, 590 gallons. But that was just the beginning. The P-38 could carry two external drop tanks under the wings, each holding either 150 gallons or 300 gallons depending on the mission profile. With the larger drop tanks, total fuel capacity reached 1,240 gallons. The engineer did the calculations. With 1,240 gallons of fuel and the P-38's cruise consumption rate of approximately 80 gallons per hour, the aircraft has a theoretical endurance of over 15 hours. The pilots listening to this briefing were stunned. 15 hours. Lieutenant Nishizawa repeated. That's impossible. No pilot can fly for 15 hours in a single-seat fighter. The physical and mental exhaustion would be incapacitating. Exactly, the engineer agreed. Which tells us that the P-38's range is limited not by fuel, but by pilot endurance. The Americans have built a fighter with more range than any human can practically use. They calculated combat radius, which was more relevant than maximum range. Combat radius accounted for takeoff, climb to altitude, cruise to target area, time in combat at high power settings, and return flight with fuel reserves. With standard 300-gallon drop tanks, the P-38's combat radius was approximately 800 to 900 miles. With larger tanks and careful fuel management, it could extend to over 1,000 miles. This meant a P-38 could take off from Port Moresby, fly 500 miles to Rabaul, fight for 15 to 20 minutes over the target, and return home with fuel to spare. The Japanese had assumed their fighters based at Rabaul were safe from fighter escort by Allied aircraft operating from distant bases. The distances seemed too great. But the P-38 made those distances irrelevant. This explains the April 18th attack, one intelligence officer said grimly. He was referring to Operation Vengeance, the mission that killed Admiral Yamamoto. On April 18, 1943, just weeks before this evaluation began, 16 P-38s had flown from Guadalcanal to intercept Yamamoto's transport aircraft near Bougainville. The round-trip distance was over 1,000 miles, almost entirely over water and enemy territory. The Japanese had believed such a mission was impossible. Fighter aircraft couldn't have the range for such a strike. But the P-38s had made the flight, intercepted Yamamoto's aircraft with perfect timing, shot down both transports, and returned to base. It was a mission that shouldn't have been possible, but the P-38's range made it reality. Yamamoto himself told us repeatedly that American industrial capacity would be decisive. The intelligence officer continued quietly. The P-38 proves he was right. They've built a fighter with capabilities that seem impossible by our standards. The fuel management system impressed the Japanese engineers as much as the raw capacity. The P-38 had multiple fuel selectors and transfer pumps that allowed pilots to manage fuel precisely between the various tanks. Drop tanks were used first, extending range while preserving internal fuel. When drop tanks were empty, they could be jettisoned to reduce drag and weight for combat. The pilot then had full internal fuel for fighting and the return journey. The system included automatic fuel transfer pumps that maintained proper center of gravity as fuel was consumed. This was crucial because the P-38's twin-boom design made it sensitive to longitudinal balance. They've thought through every detail, the lead engineer noted. The fuel system isn't just about capacity. It's about managing that capacity intelligently to maintain aircraft performance throughout the mission profile. Japanese fighters had simpler fuel systems. The Zero had tanks in the wings and fuselage, but fuel management was largely manual. Pilots had to remember to switch tanks at specific times. Forget, and you could run a tank dry and experience engine failure. The system worked but required constant attention. The P-38's fuel system was more automated. Gauges clearly showed fuel state in all tanks. Warning lights indicated when tanks were low. The transfer system worked automatically to maintain balance. Another example of reducing pilot workload, the lead evaluation pilot observed. The P-38 pilot can focus on navigation and tactics rather than constantly monitoring fuel management. The engineering team tested the P-38's actual fuel consumption under various conditions. They ran the engines at different power settings, climbed to various altitudes, and measured fuel flow carefully at economical cruise power settings around 2200 RPM and 30 inches of manifold pressure. The P-38 consumed approximately 75 to 80 gallons per hour total from both engines. This was the setting used for long-range cruise. At normal cruise power, consumption increased to about 95 gallons per hour. Still economical, but with better speed. At combat power settings above 45 inches of manifold pressure, fuel consumption skyrocketed to over 250 gallons per hour. The engines gulped fuel when pushed to maximum performance. This meant that fuel management during combat was critical. 15 minutes of hard combat at maximum power could consume over 60 gallons, equal to nearly an hour of cruise flight. The Japanese team calculated mission profiles and compared them to their own aircraft. A typical P-38 strike mission from Port Moresby to Rabaul would look like this. Takeoff and climb, 30 minutes, 30 gallons consumed. Cruise outbound at 20,000 feet, 2 hours at cruise power, 160 gallons consumed. Combat over target, 15 minutes at high power, 60 gallons consumed. Cruise return, 2 hours at cruise power, 160 gallons consumed. Landing reserves, 60 gallons minimum. Total fuel required, 470 gallons. With internal tanks plus 300-gallon drop tanks, the P-38 had 890 gallons available. This left over 400 gallons of margin for navigation errors, extended combat, or adverse winds. Zero attempting the same mission profile would be operating at the absolute edge of its range, with minimal reserves and no margin for error. Japanese pilots who flew the Rabaul to Guadalcanal missions knew this intimately. Any combat damage that increased drag, any headwinds on the return flight, any navigation errors meant running out of fuel over the ocean. P-38 pilots had enormous margins. They could afford to fight longer, take indirect routes around weather, and still return with comfortable fuel reserves. This changes the strategic calculus completely, one staff officer observed. We've been assuming that distance provides protection. Our bases 500 miles from enemy airfields seemed safe from fighter attack. The P-38 invalidates that assumption. Nowhere is safe if they can bring fighters that far. The drop tank design itself was sophisticated. The Japanese examined one of the captured tanks carefully. It was a streamlined, teardrop-shaped aluminum construction with internal baffles to prevent fuel sloshing. The attachment points used quick-release mechanisms that allowed the pilot to jettison tanks instantly when entering combat. These tanks are well-engineered, the lead engineer noted. The streamlining reduces drag significantly. And the quick-release system is reliable. The Americans understand that external tanks must not compromise combat performance once jettisoned. Japanese drop tanks were cruder by comparison. They created more drag and sometimes failed to release cleanly, forcing pilots to land with them still attached. The P-38's fuel efficiency at altitude was another advantage. At 20,000 feet, the turbocharged engines could maintain cruise power while consuming less fuel than at low altitude because the thin air required less throttle opening to achieve the same power output. Japanese engines without effective turbocharging had to work harder at altitude, consuming more fuel for less performance. This meant that high-altitude cruise, which should have been more efficient, was actually less efficient for Japanese fighters. Nishizawa flew a long-range profile test in the captured P-38. He took off with full internal fuel and 2 drop tanks, climbed to 23,000 feet, and settled into economical cruise at 230 miles per hour indicated airspeed. He flew for 4 hours, burning drop tank fuel first, then switching to internal tanks. He then conducted a simulated combat engagement for 15 minutes at high power, doing aerobatic maneuvers and high-speed runs to simulate dogfighting. After the combat simulation, he cruised for another 3 hours at economical settings before landing. Total flight time, 7 hours, 20 minutes. Fuel remaining at landing, 70 gallons, well above minimum reserves. "I could have flown another hour easily," Nishizawa reported after landing. The fuel state was comfortable throughout the mission. "I never felt concerned about having enough fuel to return." He added an important observation about pilot comfort. 7 hours is a long time in a fighter cockpit, but the P-38 is relatively comfortable. The seat is padded. The cockpit is spacious enough to shift position occasionally. There's even a relief tube system for long missions. The Americans have thought about pilot needs for extended operations. Japanese fighters provided none of these comforts. Pilots on long missions sat in hard seats in cramped cockpits, with minimal provisions for physical needs. The discomfort added to fatigue and reduced combat effectiveness. The strategic implications of the P-38's range became a major topic of discussion among the evaluation team. If American fighters could escort bombers all the way to any target in the Pacific theater, Japanese defenders would face overwhelming force at every location. The range advantage also had tactical implications. P-38s could loiter over combat areas, waiting for opportunities. Japanese fighters had to be more aggressive, engaging quickly before fuel state forced them to return to base. In actual combat, this meant P-38 pilots could be patient, choosing optimal moments to attack. Japanese pilots had to accept whatever tactical situation existed because they couldn't afford to wait for better opportunities. Real-world ace Saburo Sakai wrote in his evaluation notes from combat experience. The Americans have built a fighter that dominates not through performance alone, but through operational flexibility. The P-38 can be wherever it needs to be, whenever it needs to be there. This strategic mobility is perhaps more valuable than any single performance characteristic. The engineering team concluded their range analysis with sobering observations. Japan could not build fighters with equivalent range without sacrificing other capabilities. The Zero achieved its range through extreme weight reduction, no armor, minimal armament, and no advanced systems. The P-38 achieved similar or better range while carrying heavy armament, armor protection, sophisticated systems, and powerful engines. This was only possible through superior engine efficiency, advanced fuel management systems, and sophisticated aerodynamic design. "We cannot replicate this capability with our current technology and industrial base," the lead engineer stated in his report. The P-38's range comes from integrated system design and manufacturing quality that we cannot match. Each component, engines, fuel system, aerodynamics, contributes to the overall range capability. Copying any single element would not give us equivalent results. The fork-tailed devil could fly farther, fight harder, and return safely from missions that Japanese fighters could barely attempt. And increasingly, that range advantage was proving decisive in the vast Pacific theater. Nowhere was safe. No base was beyond reach. The P-38 had turned the Pacific Ocean from Japan's defensive advantage into America's highway for power projection, and the Japanese could do nothing to counter it. The lead evaluation pilot had flown dozens of different aircraft types during his career, but nothing prepared him for his first extended time in the P-38's cockpit. After several test flights, he spent an afternoon simply sitting in the cockpit with the engines off, examining every switch, gauge, and control. What he discovered was a philosophy of aircraft design completely foreign to Japanese thinking. The cockpit was enormous by Japanese standards. The pilot could move his shoulders freely. He could adjust his seating position. He could reach every control without stretching. There was even room beside the seat for maps, mission notes, and personal items. In his Zero, the ace flew in what amounted to a padded box. Every cubic centimeter was optimized for minimum size and weight. Moving anything except control surfaces required careful maneuvering in the confined space. The Americans designed cockpits for pilot comfort, the pilot told the engineering team. We designed them for minimum weight. The difference in philosophy is total. The seat itself was a revelation. It was adjustable in multiple directions, up and down, forward and back. Even the angle of the backrest could be changed. The cushioning was substantial, with padding on the seat, backrest, and even the headrest. The headrest included armor plating, thick steel positioned to protect the pilot's head and upper back from rear attacks. The pilot ran his hand over the armor. It had to weigh 15 or 20 kilograms. In a Zero, that much weight could never be justified for anything that didn't directly contribute to combat performance. But the P-38 carried it routinely. Every P-38. Because American designers had decided that bringing pilots home alive was more important than saving 20 kilograms. The instrument panel was a masterpiece of ergonomic design. Everything was positioned logically, grouped by function. Flight instruments in the center, directly in the pilot's primary field of view. Engine instruments to the left and right, monitoring each engine separately. Systems controls below, within easy reach. The pilot counted over 40 separate instruments and gauges. Airspeed, altitude, vertical speed, turn coordinator, artificial horizon, compass, directional gyro, clock, 2 sets of engine RPM gauges, 2 manifold pressure gauges, 2 oil pressure gauges, 2 oil temperature gauges, 2 cylinder head temperature gauges, fuel quantity gauges for multiple tanks, oxygen flow indicator, hydraulic pressure gauge, and more. The Zero's instrument panel had perhaps 15 instruments total. Basic flight instruments and minimal engine monitoring. Japanese pilots were expected to feel the engine's performance, to fly by instinct and experience rather than relying heavily on instruments. The P-38's panel told a different story. American pilots flew by numbers. They monitored everything precisely. The extensive instrumentation allowed them to operate the complex aircraft systems optimally without guessing. Look at the lighting, one of the Japanese engineers pointed out. Every instrument had its own red lighting for night operations. Switches had backlighting. There was even a rheostatic control to adjust the overall panel lighting intensity. Japanese fighters had minimal cockpit lighting. Night operations required pilots to dark adapt their vision and use small handheld flashlights to check instruments. Reading maps or navigation notes at night was nearly impossible. The P-38 pilot could read everything clearly, even on moonless nights. Another detail that seemed like unnecessary luxury but contributed to operational capability. The control yoke design was unusual compared to Japanese fighters. Instead of a center stick, the P-38 used a wheel-type yoke mounted on a column. It moved fore and aft for pitch control, rotated for roll control. The ace initially found this awkward, but after several flights, he appreciated its advantages. The wheel provided excellent leverage for roll control. It was easier to make small, precise corrections. And because it was mounted on a column instead of the floor, it didn't interfere with leg movement or take up cockpit floor space. The rudder pedals were widely spaced and adjustable. The pilot could position them exactly where his feet were comfortable. They included toe brakes for each main landing gear wheel, allowing differential braking for ground steering. The Zero's rudder pedals were fixed in position. Short pilots struggled to reach them properly. Tall pilots sat with knees bent uncomfortably. The P-38 accommodated pilots of any size. The throttle quadrant on the left console was sophisticated. 2 throttle levers, one for each engine, mounted side by side. Behind them, 2 propeller pitch control levers. Behind those, 2 mixture control levers. Each control was a different length and had a different shape at the grip, so pilots could identify them by feel without looking. This allowed single-handed engine management while the other hand remained on the control yoke. Everything is designed to reduce pilot workload, the lead engineer observed. The controls are positioned logically. They're shaped distinctively. The pilot can manage complex systems without excessive head-down time looking for switches. The electrical system was remarkably comprehensive. The P-38 had multiple generators, batteries, circuit breakers, and backup systems. Electrical power ran radios, instruments, gun heaters, pitot heat, landing lights, navigation lights, and dozens of other systems. Japanese fighters had minimal electrical systems. The Zero's electrical system powered the radio and a few basic instruments. That was all. Most systems were mechanical or manual. The oxygen system was another example of American attention to pilot needs. The P-38 had a high-capacity oxygen bottle with an automatic regulator that adjusted flow based on altitude. The pilot wore a comfortable oxygen mask with clear vision panels. Japanese fighters had oxygen systems, but they were basic. Manual flow control required pilots to remember to adjust settings as altitude changed. Forget, and you'd suffer hypoxia without realizing it. The radio system impressed the Japanese engineers enormously. The P-38 carried a VHF radio transceiver with crystal-clear audio quality. The radio could transmit and receive over 100 miles under good conditions. It had multiple preset channels that could be changed with a simple switch. The ace tested the radio during one flight, communicating with the ground station at Rabaul. Even at 50 miles distance and 15,000 feet altitude, the audio quality was perfect. He could understand every word without strain. Japanese fighter radios were notorious for poor quality. The Zero's radio was heavy, unreliable, and produced audio so distorted that pilots often couldn't understand communications. Many pilots simply turned them off to save weight and reduce distraction. The difference wasn't just technology. It was doctrine. American fighters operated as coordinated teams, with constant radio communication between pilots and ground controllers. The radio was essential to tactics. Japanese pilots operated more independently, with minimal radio communication. They relied on visual signals and pre-briefed tactics. The radio was nice to have, but not essential. Again, we see different philosophies, the lead pilot noted. Americans fight as a coordinated system with radio linking everyone together. We fight as individual warriors who happen to be in the same area. The visibility from the P-38's cockpit was exceptional. The greenhouse-style canopy provided nearly panoramic views. The pilot could see above, to the sides, and even downward through panels in the canopy frame. The canopy opened by sliding backward on rails, creating a huge opening for entry and exit. Getting in and out of the P-38 was easy compared to squeezing through the Zero's narrow canopy opening. The windscreen was thick armored glass, bulletproof, and optically perfect. No distortion, no waviness. Japanese fighters used thinner glass that sometimes had optical flaws that could be disorienting. Inside the cockpit, the pilot found numerous small details that revealed how much thought had gone into pilot comfort and effectiveness. There was a map case mounted on the left side panel. A holder for a kneeboard on the right. Clips for securing mission notes and cards. There was even a relief tube system for long missions, a simple but important feature for flights lasting 5 or 6 hours. Japanese pilots on long missions had to accept extreme discomfort or resort to makeshift solutions. The heating and ventilation system allowed the pilot to control cockpit temperature. Warm air could be directed at the feet, face, or windscreen. In the tropics, fresh air vents could be opened for cooling. The Zero had no environmental control. Pilots froze at high altitude and sweltered at low altitude. They endured it because that was expected of warriors. The P-38 treated its pilot as a valuable asset to be kept comfortable and effective. Not coddled, but provided with the tools and environment needed to perform optimally for extended periods. The survival equipment was comprehensive. The seat cushion was actually a life raft. The pilot wore a life vest. The survival kit included first aid supplies, water, signaling devices, and emergency rations. Japanese pilots carried minimal survival gear. The Warrior Code emphasized that capture was unacceptable, so extensive survival equipment seemed unnecessary. If you went down over water, you either made it to land quickly or you died. Preparation for survival wasn't emphasized. The American approach was pragmatic. Pilots were expensive to train and valuable to preserve. Give them every tool to survive if they had to bail out or ditch. Recover them, treat their injuries, and get them back in the fight. After spending hours examining every aspect of the P-38's cockpit, the lead pilot wrote a detailed section in his evaluation report that went beyond technical description to philosophical analysis. The P-38's cockpit reveals American values and priorities. They treat pilots as valuable professionals who should be given the best tools available. The extensive instrumentation, comfortable environment, protective armor, and sophisticated systems all serve to keep pilots alive and effective over extended operations. Japanese doctrine emphasizes pilot skill and warrior spirit over technical aids. We believe that true warriors should overcome hardship through discipline and training. Our aircraft reflect this: minimal comfort, basic systems, lightweight design. The question is, which philosophy produces better combat results? The answer appears to be that American pilots, given superior tools and systems, can perform effectively with less training and experience. Their aircraft compensates for skill limitations. But this creates a force that is more resilient. When American pilots are shot down, they often survive to fight again because of armor and safety systems. When they bail out, they often survive and are recovered because of good survival equipment. Their skilled pilots get more skilled. Their average pilots survive long enough to gain experience. Our skilled pilots are irreplaceable. When they die, we lose years of experience and training. Our aircraft philosophy maximizes performance but doesn't maximize pilot survival. Over time, this creates a declining skill base as experienced pilots are lost and replaced by novices. It was one of the most insightful observations in the entire evaluation. The ace understood that the P-38's cockpit design wasn't just about pilot comfort. It was about building a sustainable combat force. The Japanese approach produced perhaps slightly better performance from any individual aircraft. But the American approach produced a force that could sustain operations indefinitely, with pilots surviving longer, gaining experience faster, and remaining effective throughout extended campaigns. Lieutenant Nishizawa added his own observations after flying the P-38 multiple times. In the Zero, I feel like a warrior wielding a sword. Everything depends on my skill, my reflexes, my fighting spirit. The aircraft is an extension of my will. In the P-38, I feel like a professional operating a sophisticated weapons system. The aircraft helps me succeed. It provides information, protection, and capabilities that reduce the burden on my skill alone. I'm still important, but the aircraft is carrying more of the load. I prefer the feeling of the Zero. But I cannot deny that the P-38 approach produces effective combat pilots more quickly and keeps them alive longer. It was a brutally honest assessment. The fork-tailed devil's cockpit wasn't designed for warrior aesthetics or minimalist purity. It was designed to turn average men into effective fighter pilots and to bring them home after the fight. In a long war of attrition, that design philosophy was proving decisive. The senior engineer had spent 2 weeks examining every aspect of the captured P-38's performance. Now he turned his attention to something equally important: how it was built. He assembled a team of manufacturing specialists, metallurgists, and production engineers. Their task was to understand not just what the P-38 was, but how the Americans were building thousands of them. they began with systematic disassembly. Not just removing panels and components, but studying every rivet, every weld, every fastener. Documenting construction methods. Analyzing material choices. Understanding the manufacturing philosophy behind every decision. What they discovered was both impressive and deeply concerning for Japan's war effort. The aluminum alloys used throughout the P-38 were of exceptionally high quality. The team took samples from various structural components and conducted metallurgical analysis. The alloys showed consistent composition, uniform grain structure, and excellent mechanical properties. This is industrial-scale metallurgy at its finest, the chief metallurgist reported. These aluminum alloys are produced with tight quality control. The properties are consistent throughout the structure. There are no weak spots from impurities or improper processing. He compared it to Japanese aluminum production. Our alloys vary more in quality. We have good batches and mediocre batches. The Americans appear to have standardized their metallurgy to the point where every batch meets stringent specifications. This consistency was crucial for mass production. If materials were uniform, manufacturing processes could be optimized and standardized. Parts made in different factories would be truly interchangeable. The skin panels were fabricated from aluminum sheets of various thicknesses, depending on structural requirements. The Japanese team measured panel thickness throughout the aircraft. The measurements showed remarkable consistency. These panels were stamped from precisely rolled sheet metal, a manufacturing engineer noted. The thickness variation is less than 1%. Our sheet metal varies by 3 to 5% typically. Tighter tolerances meant better fit during assembly. Panels aligned properly without extensive fitting and adjustment. This saved enormous time during production. The riveting throughout the P-38 initially appeared crude to Japanese eyes. The rivets weren't perfectly aligned. Spacing varied slightly. But upon closer examination, the rivet installation was actually highly consistent where it mattered. Look at the rivet squeeze, one engineer pointed out, using a gauge to measure rivet head dimensions. Every rivet is squeezed to the same specification. The heads are uniform. The shop heads on the interior are consistent. This indicates automated or semi-automated riveting equipment. Japanese aircraft were still largely hand-riveted by skilled workers. Each rivet was individually squeezed by a worker using a hand-operated or pneumatic rivet gun. The quality depended on worker skill and attention. The Americans had mechanized riveting. Fixtures held parts in precise alignment. Automatic rivet guns installed multiple rivets simultaneously with consistent squeeze force. The result was faster production and more uniform quality. The fasteners used throughout the P-38 were another revelation. Almost everything used standard and Army-Navy specification hardware. Bolts, nuts, screws, washers, all to standardized dimensions and specifications. This means parts are interchangeable not just within the P-38, but across the entire American military, the lead engineer observed. A bolt from a truck will fit in a fighter. A nut from a bomber will work on a transport. Their entire military-industrial base uses common standards. Japan had multiple competing standards. Army and Navy used different specifications. Different manufacturers used different fasteners. Interchangeability was limited. The electrical wiring impressed the engineering team significantly. Every wire was color-coded according to a standardized scheme. Wire bundles were neatly organized, secured with clamps at regular intervals, and routed to avoid chafing or heat exposure. This is production line wiring, an electrical engineer explained. Workers follow color-coded diagrams. Red wire goes here, blue wire there. No expertise required. Just follow the instructions. And when maintenance is needed, any electrician can trace circuits by following the color codes. Japanese aircraft wiring was more ad hoc. Skilled electricians routed wires based on experience and judgment. Each aircraft was slightly different. Troubleshooting required expertise and familiarity with that specific aircraft. The hydraulic system components showed sophisticated manufacturing. The actuators, pumps, and valves were precision machined from high-quality materials. The tolerances were tight, but not absurdly so. Everything was designed with appropriate safety margins. "They're not pursuing perfection," a manufacturing specialist observed. "They're pursuing consistency and adequacy. These components will work reliably, but they're not made to tighter tolerances than necessary. This makes them easier and faster to manufacture." It was another example of American pragmatism. Make parts good enough to function reliably, but don't waste time and resources making them better than they need to be. The Japanese team examined the engine mounts and discovered modular construction. The mounts bolted to standardized attachment points on the airframe. The engines could be removed and replaced without custom fitting. "In our aircraft, engine installation often requires custom shimming and adjustment," a mechanic noted. "Each engine fits slightly differently. Here, any engine will fit any airframe. True interchangeability." This had enormous implications for field maintenance. American units could swap engines between aircraft quickly. If an engine failed, unbolt it, bolt in a replacement, and the aircraft was back in service. Japanese maintenance required more time and expertise. Engines were semi-permanently installed. Removal and replacement was a major undertaking requiring skilled mechanics. The quality control methods became apparent as the team examined manufacturers' markings throughout the aircraft. Almost every component had stamps, serial numbers, or tags indicating when it was made, by whom, and which batch it came from. "If a component fails, they can trace it back to the source," the lead engineer explained. "If multiple failures occur, they can identify if components from a specific production run or supplier are problematic. This allows them to improve quality systematically." Japanese manufacturing had less systematic tracking. Quality control depended more on inspector judgment than documented traceability. The team discovered inspection stamps on structural components indicating that multiple inspectors had checked the work at different stages of assembly. Critical structural areas showed 3 or 4 different inspector marks. "They're using layered quality control," a production engineer noted. "Multiple independent inspections catch errors that a single inspector might miss. It's redundant, but it virtually eliminates defects reaching the field." The surface treatments and corrosion protection impressed the Japanese team. All aluminum surfaces were anodized or primed. Steel parts were cadmium-plated or painted. Every fastener had corrosion-resistant treatment. "They're building for long service life in harsh environments," a materials specialist observed. "Tropical heat, salt air, moisture, they've protected against all of it. These aircraft will remain serviceable for years with proper maintenance." Japanese aircraft received less comprehensive corrosion protection. Parts deteriorated faster in tropical conditions. Service life was shorter. The team examined the cockpit canopy and discovered it was made from high-quality acrylic plastic, optically perfect and impact-resistant. The framing was aluminum extrusion, strong but lightweight. "The canopy alone shows sophisticated manufacturing," an engineer noted. "That acrylic sheet is thick, formed to compound curves, and has no optical distortion. That requires advanced plastics technology and precision forming equipment." The landing gear revealed precision machining and heat treatment. The main struts were forged steel, precisely machined, and heat-treated for optimal strength. The tolerances were tight where necessary for proper function, but generous where exact dimensions didn't matter. "They understand what needs to be precise and what doesn't," a machinist observed. "They don't waste effort on unnecessary precision. But where it matters, the work is excellent." The team spent days examining the propeller mechanisms. The Curtiss electric propellers used electric motors to adjust blade pitch, controlled by the propeller governors. The system was complex but beautifully engineered. "This is precision electromechanical engineering at high volume," the lead engineer said, examining the propeller hub. "These components are manufactured to exacting specifications, yet they're producing them in massive quantities. That requires advanced machine tools and skilled setup workers, even if the actual machining is semi-automated. The Japanese engineers studied the technical manuals that had been captured with the aircraft. The manuals revealed as much about American manufacturing as examining the aircraft itself. The manuals included detailed exploded view diagrams showing every part and how they fit together. Part numbers were clearly indicated. Torque specifications were provided for every fastener. Maintenance procedures were written in clear, simple language with step-by-step instructions. These manuals allow relatively inexperienced mechanics to maintain complex aircraft, the lead engineer observed. Everything is documented. Nothing is left to mechanics' judgment or experience. Follow the manual, and you can repair the aircraft correctly. Japanese maintenance relied more on experienced mechanics who learned through apprenticeship and experience. Manuals were less detailed. Experienced mechanics were essential. The team calculated production time based on their analysis of construction methods. They estimated that the P-38, despite its complexity, required approximately 15,000 to 18,000 man-hours from raw materials to finished aircraft. This was extraordinary. The P-38 was a twin-engine fighter with complex systems, yet it could be built in less time than many simpler Japanese aircraft. The difference is manufacturing method, the lead engineer explained to the assembled team. We still build aircraft largely by hand. Skilled workers fabricate parts, fit them together, adjust as needed. It's craftsmanship. The Americans have industrialized aircraft production. They use specialized equipment, fixtures, and tooling. They've designed the aircraft for production as much as for performance. Every part is made to be manufactured efficiently. He showed them calculations. Lockheed is producing approximately 50 P-38s per month at their Burbank plant. With multiple shifts, that's roughly 2 aircraft per day. This is only possible through assembly line methods and tremendous tooling investment. For comparison, Japanese factories were producing perhaps 150 Zeros per month total from all manufacturers. The Americans were producing P-38s, which were far more complex and capable, at rates approaching half the total Zero production. And the P-38 was just one of several American fighter types being mass-produced. The metallurgist provided a sobering assessment of material quality. The aluminum alloys in this aircraft are superior to what we can consistently produce. The steel alloys used in critical components show advanced heat treatment and processing. The copper in the electrical components is higher purity than our standard grades. He continued, this isn't because American metallurgists are more clever than ours. It's because their industrial infrastructure for metals production is more advanced. They have better furnaces, better refining processes, better quality control throughout their supply chain. The manufacturing team's final report was extensive and brutally honest. The conclusion was clear. The P-38 represented not just advanced aircraft design, but advanced manufacturing capability that Japan couldn't match. The P-38 is designed for mass production by semi-skilled workers using specialized equipment, the report stated. This allows America to produce sophisticated aircraft at rates we cannot match with our hand craftsmanship methods. To compete, Japan would need to completely reorganize our aircraft industry. We would need to invest in tooling, fixtures, and specialized equipment. We would need to redesign aircraft for manufacturing efficiency. We would need to develop supply chains providing standardized, high-quality materials and components. This transformation would require years and resources we don't have. Even if we began immediately, America's head start and larger industrial base mean we could never achieve parity in production rates. The lead engineer added a personal observation that captured the core issue. We Japanese take pride in craftsmanship. We believe the best products come from skilled artisans who care about their work. And for many products, this is true. But war production is different. War requires adequate quality in overwhelming quantity. The Americans have understood this. They've sacrificed artisan craftsmanship for industrial efficiency. And in this context, their approach is superior. The P-38 is not a craftsman's masterpiece. It's an industrial product, made by ordinary workers following documented procedures using specialized equipment. But it works. It works reliably. And they're making thousands of them. This is the true power of American industry. Not that they design better aircraft, though they do, but that they've created an industrial system that can turn designs into reality at a scale we cannot imagine. The manufacturing assessment was complete. The captured P-38 had revealed not just aircraft technology, but the industrial philosophy and capability behind it. And that revelation was more frightening than any performance specification could have been. By late June 1943, the evaluation of the captured P-38 Lightning was complete. The lead pilot, the senior engineer, and several other senior members of the evaluation team gathered in a conference room at Rabaul. Before them lay weeks of data, measurements, photographs, and observations. They had to distill this into a coherent assessment with actionable recommendations. "We must be honest," the lead ace began. "Many commanders don't want to hear that enemy equipment is superior. They want to hear that our pilots and our spirit can overcome any technical disadvantage. But we owe them the truth." The lead engineer nodded grimly. "The truth is that the P-38 represents a capability gap we cannot close with current resources. Not in the time frame that matters." The team worked for 3 days drafting the report. The final document was over 200 pages, but the executive summary captured the essential findings in stark terms. The P-38 Lightning is a superior aircraft to any fighter currently in Japanese service. It excels in speed, climb rate, high-altitude performance, range, firepower, and pilot protection. Its only significant weakness compared to Japanese fighters is sustained turn rate at low to medium speeds. However, P-38 tactics exploit strengths while avoiding situations where weaknesses matter. American pilots use boom and zoom attacks, maintaining speed and altitude advantage. They refuse close-range turning combat where Japanese fighters excel. When properly employed, the P-38 is nearly impossible for Japanese fighters to counter effectively using current tactics. Recommended responses require fundamental changes to Japanese doctrine, aircraft design, and operational methods. The recommendations section was carefully worded but unmistakable in its implications. Immediate recommendations: 1. Modify fighter tactics to force combat at altitudes below 15,000 feet where Japanese fighters are more competitive. Accept that high-altitude interception is currently impossible. 2. Avoid prolonged combat when P-38s are present. Their ammunition capacity and fuel reserves allow extended engagement. Japanese fighters must attack quickly and disengage before fuel becomes critical. 3. Use numerical superiority aggressively. The P-38's advantages are most effective in 1 versus 1 or small group engagements. Mass formations of Japanese fighters can overwhelm individual P-38s through sheer numbers. 4. Target P-38s on the ground whenever possible. Each P-38 destroyed on the ground eliminates a threat without risking Japanese aircraft in unfavorable air combat. The medium-term recommendations were more ambitious and more difficult. Medium-term recommendations: 1. Prioritize development of high-altitude fighter capability. This requires turbosupercharger technology or equivalent forced induction systems. Estimated development time: 18 to 24 months minimum. 2. Design next-generation fighters emphasizing speed and climb rate over maneuverability. Accept that the era of turning combat is ending. Future air combat will be decided by energy management, not turn radius. 3. Improve pilot protection in current aircraft. Add armor plating and self-sealing fuel tanks even at cost of some performance. Preserving experienced pilots is more important than marginal performance gains. 4. Develop improved oxygen systems and high-altitude equipment. Current systems limit Japanese fighter effectiveness above 20,000 feet. P-38s routinely fight at 30,000 feet. The long-term recommendations were the most radical and, privately, the evaluation team knew they were probably impossible. Long-term recommendations: 1. Reorganize aircraft manufacturing toward mass production methods. Current hand craftsmanship approach cannot match American production rates. This requires fundamental industrial transformation. 2. Invest in metallurgy and materials science. American superiority in high-temperature alloys, aluminum production, and materials processing directly enables their performance advantages. 3. Develop indigenous turbosupercharger capability. Continued dependence on imports or captured technology is unsustainable. This requires major investment in research and specialized manufacturing. 4. Accept that pilot quality alone cannot overcome technology gaps. Modify training to emphasize tactics that work with available aircraft rather than tactics that require superior equipment. The report included a classified appendix that was even more sobering. It analyzed the strategic implications of the P-38's capabilities for Japan's defensive positions throughout the Pacific. The P-38's range makes no Japanese base safe from fighter attack. Combined with America's growing bomber force, this means Japan cannot maintain defensive positions solely through geographic isolation. Rabaul, previously considered secure due to distance from Allied bases, is now vulnerable to P-38 escort missions. This pattern will repeat throughout the Pacific as American forces advance. The P-38's altitude performance means Japanese forces cannot prevent high-altitude reconnaissance or bombing. Current fighters cannot intercept effectively above 25,000 feet. This gives Americans complete intelligence advantage. Most critically, the P-38 enables America to conduct the operation we recently suffered, the Yamamoto assassination mission. Any Japanese commander, any headquarters, any facility within the P-38's operational radius is vulnerable to precision strike with fighter escort. This fundamentally changes operational security requirements. The evaluation team sent the report up the chain of command in early July 1943. Then they waited for the response. It came 3 weeks later, and it was disappointing. The response from Navy Aviation Command acknowledged the report's findings but largely dismissed the recommendations as impractical or unnecessary. Japanese naval aviation has achieved consistent victories throughout the Pacific, the response stated. While the P-38 is a capable aircraft, it can be countered through superior Japanese fighting spirit and tactical excellence. Our pilot skills remain unmatched. The response authorized some minor tactical changes but rejected the major recommendations as too expensive, too time-consuming, or requiring resources that weren't available. Turbosupercharger development. Under consideration for future aircraft, but current priorities are increasing production of existing types. Mass production reorganization. Japanese manufacturing methods have served us well. No justification for expensive retooling. Armor and self-sealing tanks. Weight penalties unacceptable. Pilot skill is better protection than armor. The lead ace read the response and felt a deep sense of frustration. They're not listening. We gave them the truth, and they chose to ignore it because they don't like what it means. The senior engineer was more philosophical but equally disappointed. The problem is that implementing our recommendations would require admitting that Japan's current approach is fundamentally inadequate. That admission is politically impossible. So they'll continue doing what they're doing until reality forces change. In practice, some frontline units did begin adapting tactics based on the evaluation findings, even without official sanction. Experienced squadron commanders who read the report or heard about its conclusions began modifying their approach to combat with P-38s. They stopped trying to dogfight the Lightning. They learned to attack from below when possible, where the P-38's altitude advantage was negated. They practiced quick hit-and-run attacks followed by immediate disengagement. They used weather and cloud cover more aggressively to negate the P-38's speed advantage. These adaptations helped somewhat. Japanese losses to P-38s decreased slightly as pilots learned what not to do. But the fundamental problem remained. The P-38 could usually choose whether to accept combat or not, and Japanese fighters couldn't force engagement. The captured P-38 itself remained at Rabaul for several more months. It was flown occasionally for demonstration purposes, showing pilots what they were up against and how P-38s maneuvered. In October 1943, As American forces advanced and Rabaul came under increasingly heavy attack, orders came to destroy the captured P-38 rather than risk it falling back into American hands. On October 15, Japanese personnel drained its fuel, removed useful components for further study, and burned what remained. The fork-tailed devil that had taught the Japanese so much was reduced to charred metal and ash, but the lessons remained. And increasingly, those lessons were being validated by combat results throughout the Pacific. By late 1943, P-38s were appearing in growing numbers everywhere. They escorted bombers to targets Japanese commanders had thought were beyond fighter range. They conducted long-range fighter sweeps that caught Japanese aircraft by surprise far from their bases. They provided air superiority that enabled American ground and naval operations. The evaluation team's predictions were proving accurate. But Japan's response remained inadequate. Some Japanese aircraft companies did begin work on improved designs incorporating lessons from the P-38 evaluation. The Kawasaki Ki-61 featured a liquid-cooled engine, though without turbo-supercharging. The Nakajima Ki-84 emphasized speed and climb over pure maneuverability. The Kawanishi N1K-J tried to match P-38 speed while retaining Japanese maneuverability. These aircraft were improvements over earlier designs. But they arrived late, in small numbers, and still didn't match the P-38's altitude performance or range. And by the time they reached combat units, the Americans were fielding even more advanced fighters like the P-47N and P-51D. Japan was running a race it had already lost, trying to match American aircraft from 1943, while America moved on to designs for 1944 and 1945. The famous Saburo Sakai continued fighting throughout the war, eventually surviving to write his memoirs. In them, he reflected on his experiences fighting the P-38. I had full confidence in my ability to destroy the P-38, but to do this I had to get in close and start my firing run from below the enemy's tail, he wrote, highlighting the tactical puzzle the P-38 presented. The lead engineer, Jiro Horikoshi, survived the war as well and became one of Japan's most respected aeronautical engineers. In his post-war writings, he reflected extensively on the lessons learned from American designs. We learned that we had been designing aircraft for the wrong war. We designed for short-range combat over our home islands. America designed for long-range combat over the vast Pacific. We designed for minimum weight. America designed for maximum capability. In every case, the American approach proved superior for the war that was actually being fought. The captured P-38 evaluation had been a moment of clarity that came too late. The burned wreckage of the captured P-38 Lightning sat on the Rabaul airfield for weeks after its destruction in October 1943. Eventually, advancing American forces would overrun the position, and the twisted metal that had once been the fork-tailed devil would be bulldozed aside and forgotten. But the impact of that single captured aircraft would echo through the rest of the Pacific War and beyond. The evaluation conducted by the Japanese pilots and engineers represented one of the most thorough analyses of enemy equipment undertaken by any nation during World War II. Over 6 weeks of intensive study, they had learned everything there was to know about the P-38 Lightning. They had flown it extensively, understanding its performance envelope completely. They had disassembled it systematically, examining every component and system. They had analyzed its manufacturing methods, revealing the industrial philosophy behind American aircraft production. They had tested it against their own fighters, confirming what combat pilots had reported about its capabilities. And they had written a comprehensive report that told Japanese leadership exactly what they were facing and what needed to be done to counter it. The tragedy was that the report's recommendations were largely ignored. By late 1943, Japan was locked into strategies and production systems that couldn't be changed quickly. The industrial infrastructure was committed. The training pipeline was established. The tactical doctrine was ingrained. Making the fundamental changes the evaluation team recommended would have required admitting that everything Japan had built its air war strategy around was becoming obsolete. That admission was politically and psychologically impossible for many Japanese leaders, so the war continued with Japan trying to fight American technology with Japanese spirit, trying to counter American production with Japanese craftsmanship, trying to match American innovation with Japanese tradition. It didn't work. The P-38 Lightning went on to become one of America's most successful fighter aircraft in the Pacific theater. It served in every major campaign from the Aleutians to the Philippines. P-38s shot down more Japanese aircraft than any other Allied fighter type in the theater. The statistics tell the story. P-38 pilots claimed over 1,800 aerial victories in the Pacific. America's two top aces of the war, Richard Bong with 40 victories and Thomas Maguire with 38, both flew P-38s exclusively. The aircraft that Japanese engineers had studied so carefully at Rabaul was being mass-produced in quantities they could barely comprehend. Lockheed would eventually build over 10,000 P-38s in various versions. This represented more total P-38s than Japan produced of any single fighter type during the entire war. The tactical lessons from the captured P-38 evaluation did filter down to frontline units, even without official endorsement. Japanese pilots learned not to dogfight with P-38s. They learned to attack from below when possible. They learned to disengage quickly before the P-38's advantages in speed and altitude could be brought to bear. These adaptations helped individual pilots survive longer. But they couldn't change the strategic reality. The P-38 could operate wherever it chose, and Japanese fighters couldn't prevent it. As the war progressed, the P-38's role evolved. In 1944 and 1945, as newer American fighters like the P-51 Mustang and F-4U Corsair took over air superiority missions, the P-38 increasingly focused on ground attack, reconnaissance, and night fighting. Its twin-engine reliability made it ideal for long, over-water missions. Its stability made it an excellent platform for cameras and specialized equipment. But for Japanese pilots who had faced it in combat during 1943 and early 1944, the P-38 remained the fork-tailed devil, the aircraft that had announced America's technological supremacy in the Pacific skies. The real Saburo Sakai survived the war as well, despite being wounded multiple times and partially losing his vision in one eye from combat injuries. He became an author and motivational speaker in post-war Japan, often discussing his experiences fighting against the P-38. In his memoir, Samurai, Sakai wrote, "The P-38 was an amazing aircraft. Flying it, a pilot could begin to understand why we were losing the air war. It wasn't because American pilots were better than us. Many of them were novices with minimal training. But they flew aircraft so superior that their lack of experience mattered less." I often wondered what would have happened if we Japanese had been given P-38s and the Americans had been forced to fly Zeros. I believe the outcome would have been reversed. The aircraft mattered more than the pilots, though we didn't want to admit it at the time. The captured P-38 evaluation influenced Japanese aircraft design in the war's final years, though the impact was limited by Japan's declining industrial capacity. The Mitsubishi J-2M Raiden and Kawanishi N-1K J Shurden were designed with lessons from the P-38 in mind, prioritizing speed and climb over pure maneuverability, incorporating better pilot protection, and attempting to match American altitude performance. These aircraft were good designs, but they arrived too late and in too few numbers. Japan's industry was collapsing under American bombing and blockade. Experienced pilots were dying faster than new ones could be trained. Fuel shortages grounded aircraft even when they were available. By 1945, Japan was fielding pilots with less than 100 hours of training, flying outdated aircraft, with minimal fuel for combat. Meanwhile, American pilots had hundreds of hours of training, flew cutting-edge aircraft, and had virtually unlimited fuel and ammunition. The technological and industrial gap the P-38 had revealed in 1943 had only widened. The legacy of the captured P-38 extends beyond the Pacific War. It represented a watershed moment in aerial warfare, demonstrating that aircraft design had evolved beyond the pursuit of pure performance to encompass systems integration, pilot support, and manufacturing efficiency. Post-war fighter design incorporated many lessons the P-38 embodied. Jet fighters would prioritize speed and altitude performance. They would include sophisticated systems to reduce pilot workload. They would be designed for production as well as performance. They would protect pilots with armor and ejection seats. They would mount weapons for maximum effectiveness rather than aesthetic appeal. The P-38's twin-boom design was largely abandoned in favor of more conventional layouts for jet fighters, but the philosophy behind it, solving engineering problems through innovative design rather than accepting limitations, became standard practice. For Japan, the P-38 evaluation was a moment of clarity that came too late. By mid-1943, when the evaluation was completed, Japan had already lost the initiative in the Pacific War. Guadalcanal had fallen. The Solomon Islands campaign was turning against them. Japanese naval aviation was suffering irreplaceable losses. The captured P-38 confirmed what some Japanese officers already suspected: they were fighting a war they couldn't win through military means alone. America's industrial capacity, technological sophistication, and systematic approach to warfare were overwhelming Japan's warrior culture and skilled craftsmanship. In the decades after the war, as Japan rebuilt and eventually became an economic powerhouse, some of the lessons from the P-38 evaluation influenced Japanese industrial development. The emphasis on quality systems, standardization, and continuous improvement that became hallmarks of Japanese manufacturing echoed some of what the evaluation team had observed in American aircraft production. The engineer Jiro Horikoshi noted this irony in a 1970s interview. "We studied the P-38 to understand how to defeat it. We failed at that. But in studying it, we learned principles about industrial production, systems integration, and quality management that Japan later applied to automobiles, electronics, and other industries with great success." Perhaps the P-38's greatest contribution to Japan came after the war, not during it. Today, only a handful of P-38 Lightnings remain airworthy, cherished by collectors and airshow enthusiasts. They're beautiful aircraft, with their distinctive twin booms and polished aluminum skin gleaming in the sun. Watching one fly, hearing the rumble of its twin Allison engines, it's easy to understand why it earned respect from friends and foes alike. But for the Japanese pilots and engineers who examined that captured P-38 at Rabaul in 1943, it represented something more than beauty or performance. It represented a reality they couldn't change, that they were fighting an enemy whose technological and industrial advantages were insurmountable. The fork-tailed devil had been captured, studied, and understood. But understanding it didn't diminish its effectiveness or change the war's outcome. Knowledge without the ability to act on that knowledge is just painful awareness of inevitable defeat. In the end, the captured P-38 served as both a remarkable piece of intelligence and a harbinger of Japan's fate. It showed Japanese aviation experts exactly what they were facing. It revealed American capabilities in stark detail. It provided tactical insights that saved some Japanese lives, but it also showed them a future they couldn't prevent: American aircraft growing more numerous and more capable, while Japanese aviation withered under the pressure of losses it couldn't replace and technology gaps it couldn't close. The report sat in Japanese archives, gathering dust as the war ground on toward its inevitable conclusion. The pilot's insights, the engineer's analysis, and the evaluation team's recommendations were all there, documented in meticulous detail. But by the time anyone might have acted on them, it was already far, far too late. The P-38 Lightning had revealed all its secrets to Japanese engineers. And in doing so, it had revealed the largest secret of all, that this war would not be won by warrior spirit or tactical brilliance, but by industrial capacity and technological superiority. And in that contest, Japan had already lost before the first shot was fired. The fork-tailed devil had shown them the truth. They just couldn't bear to accept it until the smoking ruins of their cities and the surrender papers on the deck of the USS Missouri made it undeniable. If you enjoyed this story and want to support the channel, please consider liking this video, subscribing, and hitting the notification bell for more untold tales from World War II. Check out our other videos on the P-38 Lightning's combat record, including the Yamamoto assassination mission and the incredible stories of America's top aces. Thank you for watching the War Archives. Until next time, remember, history teaches us if we're willing to learn.